If your IGCSE Physics Paper 4 exam were tomorrow and you have only one video to watch, let me tell you, this will be it. Many students revise everything, but they still lose marks. Do you know why? Because they revise the wrong things. Every year, Physics Paper 4 repeats the same patterns, same ideas. So if you know what examiners love to test, you can gain 10 to 20 extra marks without studying more. So in this video, I have condensed the most tested concepts, formulas, definitions, as well as the explanations that appear again and again in IGCSE Physics Paper 4 and now align with the new 2026 to 2028 syllabus. This is not a full lesson. Bear this in mind. It is not a full lesson. This is the final boost, the exact physics knowledge examiners expect you to recall under so much of the pressure. So grab your pen, download the PDF in the description, and let us begin. So this is it, Final Boost, IGCSE Physics Paper 4, 2026 to 2028 syllabus. So let us get started. So first thing, physical quantities and measurement techniques. So when we talk about the measurement technique, the physical quantities that we are supposed to measure, we need to look into the right apparatus. So the apparatus that are very important are meter rule, stopwatch, measuring tape, and measuring cylinder. These four apparatus are so very important. Right, now let us look at this apparatus one by one. Meter rule is used to measure length, measure distance, or even height. Sensitivity means the smallest division of the meter rule. The smallest division of the wooden meter rule is just like the smallest division of your cm rule, which is 0.1 cm. And the units that can be measured by meter rules are meter, centimeter, or millimeter. Measurable length. Meter rule can only measure up to 1 meter or maximum of 100 cm. So you bear that in mind. This is one of the limitations of the meter rule. The next one is measuring tape. Measuring tape works the same way as meter rule. It is used to measure length, measure distance, or height. And the sensitivity is exactly the same as meter rule. It is 0.1 cm. The units measured by measuring tape are cm, meter, or millimeter. So what is the function of the measuring tape? Measuring tape is used to counter the limitation of the meter rule. Okay, the lack of the meter rule. So meter rule, remember, meter rule can only measure up to 100 cm. Measuring tape can measure more than 1 meter. So if you see that a diagram is being given or the information given by the question saying that you have to use an apparatus to measure 2.5 meter, 6.7 meter, so you know you have to name the right apparatus. The right apparatus to be used is not meter rule, but measuring tape. Now, measuring cylinder. Measuring cylinder is used to measure volume. Right? It could be measure volume of the liquid or volume of the small irregular shaped object. So I'm going to write that down, volume of liquid or volume of small irregular shape object. So the object must be small enough to fit into the measuring cylinder, right? Of course, if you want to measure the volume of a small irregular shaped object, you have to make sure you need the help of the liquid or you need the help of the water. So the unit measured by measuring cylinder in the lab is normally cm cube. Now, okay, one of the question, how to measure the volume of the liquid, okay? Maybe 2 marks, maybe 3 marks will be given to that. So first thing, you have to suggest the right apparatus. The right apparatus to be used is your measuring cylinder, right? So first thing, prepare measuring cylinder. Prepare a measuring cylinder. Second, okay, pour liquid into measuring cylinder. And you know that, let me show you the liquid level. Let's say this is a liquid level. Of course, the liquid level would not be horizontal, right? It will be something like this, curve like this, a bit curvy, a curve like this. This is called meniscus. So whenever you take the reading, you make sure that you lower your eye level to the reading below that meniscus. So you have to make sure your eye level, this is my eye. Lower your eye level into, okay, towards the reading below the meniscus. This is called meniscus. The curve is called meniscus. Okay. Take reading below meniscus. That's how you measure the volume of a liquid. Right, feel free to pause the video to write down the answer. Now, the next one, how to measure the volume of irregular shaped object. What do they mean by irregular shaped object? Irregular shaped object is the object, okay, it's like the shape of the rock. You don't have a specific shape. That is called irregular shaped object. So if you want me to draw a diagram, definitely I would draw it. So I'll draw a diagram first. You prepare an irregular shaped object. First thing you do, you have to use your measuring cylinder. This is my measuring cylinder. And then you fill in water into the measuring cylinder. How much water to be filled in is entirely depending on you. Okay, so you don't fill in 2 liters of water and don't fill in too much of the water. Just nice, okay? I just fill in. And then once you fill in the water, you are going to take the initial reading on the measuring cylinder. That will be the volume of the water. And what happened next is that you place the irregular shaped object into the measuring cylinder. And you definitely know that the reading, the water level is going to rise out due to this irregular shaped object. So you take the final volume of the measuring cylinder on the measuring cylinder. And then you find the difference between the two volumes to get the volume of the irregular shape. Because the final volume, red, okay, given by the measuring cylinder, that will be the volume of the liquid or volume of the water plus the volume of the irregular shape object. Right, so I'm going to write down the step. Okay, first one, fill water into measuring cylinder. And what happens next? Take its initial volume. This is very, very important. Second, carefully place irregular shape object into measuring cylinder. Take its final volume. Now the third step, volume of irregular shape object is equal to final volume minus initial volume. That's it. So the key points are, I want to see this, fill water. I want to see you suggest the correct apparatus. And then you take initial volume. Want to see that? And then you place irregular shape object into the measuring cylinder, take the final volume. And the last part, you have to tell us how do we calculate the volume of the irregular shaped object. So you can also write the volume of the irregular shaped object will be the difference between the two volumes, right? Now, move on. Stopwatch. Have you ever seen stopwatch in the lab? The stopwatch in the lab right now is being replaced with the digital stopwatch. We don't really use the analog stopwatch anymore because digital stopwatch will be more accurate in measurement, more sensitive, right? So stopwatch is used to measure short period of time. So the sensitivity of the digital stopwatch will be 0.01 second. And the units, second, minutes, these are the units measured by the stopwatch. Now, how to determine the period of the simple pendulum? Do you know what is pendulum? It is a pendulum bob which is tied to a string. And then, okay, you just attach it to a clamp. You just clamp it so that it is vertically downwards like that. But if you want to measure the period, okay, let me explain period first. Period means the time taken for one complete oscillation. Okay, maybe you want to ask, what do I mean by one complete oscillation? Oscillation means that, okay, this is how we measure oscillation. Let's say the initial position of the pendulum is at A. If you want the pendulum to swing, don't you think that you have to displace the pendulum? So yes, I would displace the pendulum to one side. Maybe I displace to C. Okay, so I start from C and I let it go entirely. So what happens to the pendulum is that the pendulum will swing back to A, swing even higher than A, reaches B, and then from B back to A, and then back to C. So if your angle, the angle that you displace is very small, you will see that the pendulum will swing back to almost equivalent to C. That is called one period. So one period, okay, one period is from time taken from C to A to B to A back to C. That is called one period, right? But you see, right, there are so many resistive forces exist in our daily life, like air resistance, right? When you displace the pendulum, you definitely don't take just one period because you have to respond very fast. You have to conduct this experiment by yourself individually. So when you let it go and then you have to prepare to stop your stopwatch and start your stopwatch and stop your stopwatch, and due to the human's reaction time, right? If you only take one period, right, the time of measurement of period will be super duper inaccurate. So how do we make sure our measurement of period will be as accurate as possible? One thing, we calculate the period. We don't measure the period by using the stopwatch. Huh? What is that? Okay, don't worry. You just displace, okay, to C first, and then you let go the pendulum. So what happened? So this pendulum will move from C to A to B to A back to C. You time for 10 complete oscillation. Time 1, 2, 3, 4, 5, 6, 7, 8, 9, and prepare to start your stopwatch. 10. Okay, when it come back, press the stopwatch. Just stop it. So that will be, right, more relaxed for you. You don't have to rush. Okay, so your human reaction time could be greatly reduced. Even when you let it go, firstly, when you let it go, let the pendulum bob, right? Let the pendulum swing. You don't press the stopwatch right away. You let it swing first, maybe for one complete oscillation or two complete oscillation. Then only you comfortably press the stopwatch. And then you time 10 times and then press the stopwatch to stop the stopwatch. Right? So I'm going to write that down here. First step, okay, displace pendulum at small angle. Maybe you wonder, what is small angle? Small angle is between 5 degrees to 10 degrees, right? And then, okay, and let the pendulum swings freely for 2 complete oscillations. Press, okay, or you say start the stopwatch. Instead of press, you can say start the stopwatch. And time for 10 oscillations. Third, stop the stopwatch and record the time. And then fourth, period is equal to time taken for 10 complete oscillations divided by 10. Done. So the key points are displace pendulum, small angle, we want to see that. And then start the stopwatch, time for 10 oscillation, and then period is equal to time taken for 10 complete oscillation divided by 10. So if you want your measurement of period to be as accurately as possible, you calculate the period instead of you use the stopwatch to time your period. Now, the next one, that is about physical quantities. Physical quantities can be divided into 2 big groups. One is called scalar quantities. The other one is called vector quantities. Okay, in paper 4, the question normally asks you to state what is meant by scalar quantity and give examples. Or state the difference between scalar and vector quantities and give example for each of them. Right? That could also be the question. Okay, so you have to understand what is meant by scalar quantity. The definition of scalar quantity is a quantity which, okay, consists of magnitude only. So we want to see this keyword, magnitude only. So what do I mean by magnitude only? Magnitude only meaning to say that you have a value and an appropriate units. Like for example, I'm walking for 10 kilometer. That is a scalar quantity. I am walking 10, I am running at 100 kilometer per hour. That is also a scalar quantity because that is only magnitude, the value together with the appropriate unit. So the examples of the scalar quantity are maybe speed, distance, temperature. I give you more. Time. What else? Pressure. Volume, density, etc. Now, vector quantity. Okay, vector quantity is a quantity which consists of both magnitude and direction. So the key point is both magnitude and direction. We want to see that. So the examples of the vector quantity are velocity, displacement, force, okay, or you can write weight, gravitational force, upthrust force, okay, all the forces are, I don't want to give you so many forces, upthrust force, resistive forces, those are called vector quantities, right? And then maybe, what is that? Yeah, momentum, acceleration, etc. So let me give you one example on how to differentiate between vector and scalar quantity. Let me tell you this. Okay, I am walking 1 kilometer. Full stop. The other situation is that I am walking at 1 kilometer towards east. You see that? East is a direction. So vector quantity is a quantity that gives you more information. So you will be wondering, oh, this person is walking 1 kilometer towards east. Where is this person going? So you basically can guess. You see that? So because I give you more information. But for a scalar, I can only tell you I am walking at a certain distance. That's all. Full stop. See the difference? Right. Now, another thing that you should bear in mind is that, okay, how to calculate the resultant vector. The vector required in your syllabus are, the vector required in your syllabus are force and velocity and no others. Right, so you need to know how to calculate resultant force or resultant velocity as well as, okay, resultant velocity. So we can use two methods. Either you use mathematics calculation, maybe you have to bring in Pythagoras theorems, etc., right? Or graphic calculation. So we are going to look into these one by one. Now, graphic calculations, right? You can choose two methods to use. Whether graphic means drawing. So if I say drawing, you have to prepare your protractor, your ruler, your CM rule, your pencil, right? So that you can draw as accurately as possible. Drawing means you have to draw accurate. Sketching means you just sketch, right? Without the actual value. Right, there are two methods, right? One is to draw vector triangle, the other one is to draw parallelogram. Let us look into these one by one. Vector triangle, the rule is super duper simple. You just remember one row, right? To find the resultant vector, the rule, right, when you draw a vector triangle is tip to tail rule. What is that? I never heard before. Yes, okay, some of the students might not heard this before, but I'm going to give you the easiest way to remember, right? What do I mean by tip to tail rule? I want you to imagine an arrow. This is an arrow. The pointy part of the arrow is called the tip of the arrow, and the back of the arrow is called the tail of the arrow. Let me give you more example. How about that? Okay, I'm going to draw. I'm going to give you example. Example. I have two forces, for example, maybe, okay, one force, okay, horizontal, not this horizontal force. Okay, let me draw it again. Okay, this is horizontal line. Okay, let's say I have this force, okay, 10 Newton, for example, and then this is 20 degrees, for example. And then, okay, there's another force which is acting, okay, plus with this force. 6 Newton, for example. Find the resultant force. Okay, if you use the graphic method and you use a vector triangle, this is the solution. Okay. First of all, okay, it is totally your choice which force that you want to draw first. Okay, if you want to draw the 10 Newton first, you have to use your protractor, right? You measure, okay, horizontally, and then you measure at 20 degrees. Okay, when you draw a vector triangle, whether this is a scale diagram, if this is a scale diagram, you have to give the scale. So I'm giving you the scale, 1 cm on my cm rule represents 1 Newton. How about that? So I need to use my ruler to draw. Okay, so sorry. I have to use my cm rule to draw, measure at 20 degrees. You have to use a protractor, and then you use your meter cm rule to draw, 10 cm. And this is 20 degrees. And then I want you to pay special attention when you use a vector triangle. Look at the tip. This is called the tip of 10 Newton. So you have to join. Oh, I need to draw nicely. So you have to join with the tail. Let me redraw it. So this is it. Okay, this is 20. Okay, this is 10 Newton, for example. 10 cm right here, this is 20 degrees. So the tip of the 10 Newton must be joined with the tail. The tail of 6 Newton. So you measure, where's the tail? Oh, the tail is here. So you measure 6. I use different colors so that you can see. Okay. Okay. Shorter a bit. Okay, this is called tip to tail rule, 6 cm right here. And then how to determine, right, the resultant force? The resultant force must start from the tail, the first force that you draw, and then all the way. Okay, I'm going to use an annotation to show you. Okay, you have to draw all the way to meet the tip of the second force. This is called resultant force. And then you just need to measure and convert to Newton. This is it. This is what we call vector triangle by following the tip to tail rule to determine the resultant force. Okay, if you don't want to draw this triangle, never mind. If you prefer the 6 Newton, okay, fine. You can draw the 6 Newton first. So I'm going to measure, start from here, 6 cm, for example. Okay, this is my 6 cm. And then from here, you have to draw this tip of the 6 Newton must be joined with the tail of the 10 Newton. So you draw a dotted horizontal line in order for you to measure the angle as accurately as possible. And then you just need to measure 10 cm. And this is, of course, 20 degrees. And then your resultant vector would be, okay, from the tail of the first force that you draw all the way to meet, okay, the tip of the second force. So measure this distance. This is distance, you change it to Newton. This is the resultant force. Can you see? This is called tip to tail rule. So you might wonder, hey, these two triangles are different. Of course, they're different. But I want you to pay special attention to one. Direction of the resultant force is the same. So regardless of which force that you start first, it doesn't matter. It will give you different types of triangle. But at the end of the time, you will get the same direction for the resultant force. So no worries. Right? So if you have any hesitation, any questions, and any doubts, and you still have questions about this, do not hesitate. Just comment below. Right? The next one is called parallelogram rule. Parallelogram. Okay, let me use the pen first. Parallelogram, the rule is that it is tail to tail rule. So imagine an arrow. This is the tip of the arrow. The back of the arrow is the tail of the arrow. So I'm still going to use the previous example to show you. Example, let me see. Okay, this is 10 Newton. 10 Newton, this is 20 degrees plus 6 Newton. So if you want to use the parallelogram method, we write down the scale first. Solution. Maybe use the same scale. 1 cm is equal to 1 Newton. Right. Parallelogram is simple. Now you draw, okay, horizontal dotted line so that you can measure your angle as accurately as possible. And then you measure your angle of 20 degrees. Draw 10 cm. 10 cm. This is 20 degrees. See that? Tail to tail. Okay, fine. Where is the tail of the 10 Newton? It is here. Join with the tail of the 6 Newton. So I'm going to join it like that. Okay, like this. Okay, and then this one seems to be okay. I need to draw with another angle because this one, okay, it is more to vector triangle. Never mind, I just changed this one. Okay, I just changed this 6 Newton to horizontal direction. How about that? Okay, so that it's easier for me to explain. So this is 6 Newton. So now draw again. Okay, this is 10 cm. This is 20 degrees. Okay, identify where is the tail. Okay, the tail of 10 Newton is there. So I need to join with the tail of the 6 Newton here. Draw 6 cm. 6 cm. Can you see? That is called tail, mid-tail. And then after that, you have to measure a line which is parallel to the 6 cm. It's still 6 cm. And then another line which is parallel to the 10 cm, still 10 cm. Okay, this is 10 cm. And then if you want to determine resultant force, it is from the tail, mid-tail, all the way to tip, mid-tip. This is the direction of the resultant force. And you just need to measure the length and convert it to Newton. That's it. Okay, now we move on to the next one. Motion. Motion is related to how fast the object is moving or how slow object is moving, whether the object is accelerating or object is not accelerating. So first one, you need to know how to define speed. Speed is being defined as distance per unit time. Remember, speed is a scalar quantity because both distance and time are scalars. What about velocity? Velocity is being defined as displacement per unit time. Velocity is a vector quantity because displacement is a vector. Define acceleration. This is very important. Okay. If you ask me to compare, this is the most important. Define acceleration. Acceleration is being defined as the rate of change of velocity. Some of the students put acceleration as the change in velocity. That is wrong. That is not acceleration. If you don't want to put this definition, rate of change of velocity, you can change it to change in velocity per time. Okay. Or change in velocity per time taken. Or if you don't want, fine, no problem. You can write this. Final velocity minus initial velocity per time. Done. And average speed. Average speed is being defined. Average speed can only be calculated to go. So you have to find the total distance divided by the total time. Right? Don't be confused. If I give you higher speed and lower speed, you don't just add out the two speed and divide it by 2. That is not the way we calculate the average speed. It has to be calculated by only one formula. You have to find the total distance of the journey divided by the total time in order for you to get the average speed. Now, graph, okay? You can get rid of the graph. Don't you think in physics, right? Most of the time, right? More than 80% graph would be on your first question of paper 4. So there are two graphs that you need to know, right? What are the two graphs? The two graphs are distance time graph and the speed time graph. Whenever a graph is being given, you just bear this in mind. In physics, when a graph is being given, you can obtain two information. What are the two information? The two information are area of the graph, area under the graph, or the gradient of the graph. Only these two and no others. Okay, so if this is a distance time graph, okay, they have to label here as distance, and this is a time. So what can you get from the graph? Remember this, you can only find gradient, you cannot find area. Gradient of the graph represents the speed or how fast the object is traveling. So if this is a speed time graph, look at the y-axis. If the y-axis is speed, focus on y-axis. If the y-axis is speed, then the gradient, you can find both gradient and area. The gradient of the graph represents acceleration. And the area of the graph represents the total distance traveled. I would say if you ask me to compare between distance time graph and speed time graph, I would say speed time graph is way more important. Why way more important? Because you can find both gradient and area. Now, let us look at type of graphs here. Maybe you wonder, okay, how to find the gradient, right? This graph, okay, whether it is a speed time graph or it is a distance time graph, you see this horizontal line? This graph is called horizontal line graph. Horizontal line, you have to understand, okay, the shape of the graph. Horizontal line graph, the gradient will always equal to 0, no gradient. Is that okay? If this is a distance time graph, the gradient is 0. That means that, okay, object has no speed. You see, look at gradient of the graph represented by distance time graph. Right? If the graph is horizontal, gradient is equal to 0. Since this is a distance time graph, the gradient is actually representing the speed. So since the object has no speed, the object is not moving. But if this is a speed time graph, that means the object is moving with a constant speed. Why? Because the gradient is equal to 0 and object has no acceleration. See that? Now, the second graph, okay, this graph is called, okay, this graph is called a straight line graph. So for a straight line graph, just remember the gradient is always constant. Object is moving at constant speed or object is moving at constant acceleration, depending on the y-axis. And then the area of the graph, if this is a speed time graph, the area is the area of triangle. So area of triangle is half times length times height. And this graph is called linearly increasing graph. Linear graph, right? Or you call it as linear graph, no problem. The gradient is also constant. Sorry, lack of T. But the area of the graph, remember, right? This is the area of trapezium. Area of trapezium. That's the difference. So the area of trapezium, half A plus B times the height. Remember that. That's all. Now this graph, the first graph is called a curve graph. Remember when you see curve graph will never give you constant gradient. Why? To find the gradient, when you learn math, to find the gradient, you know that you have to draw tangent. What is tangent? Tangent is you mark, okay, at any points on the graph. Don't just mark one point, mark more than that. And then once you have already made your mark, you draw a line. A line that is called tangent line. Tangent line is a line, a straight line, which must pass through the point that you labeled. Can you see that my tangent line is getting more straight, more vertical, or more towards y-axis? That also means that the gradient is increasing. See that? For this graph, it is also a curve graph, but I want you to see when I mark the points here, okay, and I draw my tangent. Look at my tangent, my straight line, the one that, okay, I draw with red color. You could see that the red lines are getting more towards the x-axis, more horizontal. So this also means that the gradient is decreasing gradient. That's all you have to remember. Now, move to free fall. Okay, free fall, normally they would love to ask you to explain the free fall, right? Let me give you the summary of free fall. Free fall, basically, you can consider two different situation. One situation is without air resistance. The other situation is with air resistance. So if you see the question mentioned that, okay, this is a free fall without air resistance, you have to remember this. All objects, regardless of their masses, whether heavy object, light object, it doesn't matter, okay? Heavy, light object, big or small, right, will fall, okay, with the same gravitational acceleration. If this experiment is conducted on Earth, then the gravitational acceleration will be 9.8 meter per second square. Okay, so if the objects are dropped without air resistance, yeah, let's say this is a building, I drop a small object and a big object A and object B. So when these two objects, okay, regardless of their mass, regardless of their sizes, right, masses, sizes, when they are being dropped at the same height, right, both of them will fall and reach the ground at the same time. Okay, when objects are dropped from the same height, they will reach the ground at the same time. Done. Okay? Now, with air resistance is different, right? So how different is different? I want you to see this. You know, right? You try this, okay? If you want to test, you try to walk, okay? Maybe 200 meter, okay? Just walk with the constant pace, right? With your comfortable speed, okay? Walking, slow speed, remember? And then you try to run the same distance, 200 meter with full speed, okay? Won't you feel tired as compared to walking? Yes, right. When you run at full speed, you know that your speed increases, right? So you feel like more wind, okay, is opposing you. That's not wind, that's air resistance trying to oppose your motion. Air resistance is the blocking by air particles that cause you, okay, to feel more tiring. So air resistance, you have to remember one thing. Air resistance increases with speed. When you move slowly, low air resistance will add on you. But if you move faster, right, there will be a great air resistance acting on you. That is why you feel more tiring. See that? So I'm going to explain how air resistance, because the question normally will ask, okay, um, what happens to the speed of the object is being dropped from a certain height and air resistance is acting on the object. Okay, describe in terms of forces or acceleration, right? I will discuss both. Now, I want you to remember I draw something here. Okay, now is this okay? I will just explain. So these are the standard answers, yeah? At the start of the fall, I will highlight the keyword. Okay, object is at rest. When the object is at rest, okay, the only force acts on object is its weight. So, okay, object accelerates, okay, with 9.8 meter per second square towards the ground. And then, different color. When the speed of object increases, air resistance increases, resultant force on object decreases. Okay, acceleration decreases. And then after that, at one point, object, okay, speed of the object, speed of object reaches maximum. Air resistance balances weight of object. Okay, what happens? Resultant force on object is 0. Okay, and then we say that object falls with terminal velocity. What is terminal velocity? Terminal velocity is the maximum velocity of a falling object when air resistance, right, balances the weight of the object. So no increase in the acceleration, object will fall with the same velocity until it reaches the ground. So now let me highlight the key points for you. So you need to mention step by step. If this is about description question, you have to mention what happened first and then what happens next, right? So at the start of the fall, object is at rest, or you can say the speed of the object is minimum. So that is why I say air resistance acting on the object is equal to 0, because air resistance acts, okay, is depending on the speed of the object. The only force is the weight. You see, I mentioned the force. If the question asks you to mention the acceleration, you need to mention that object will accelerate at gravitational acceleration, okay, of 9.8 meter per second square. So when the speed increases, what happens? Air resistance will also increase. So when the air resistance increases, air resistance is the opposing force by the air particles that trying to oppose the motion of the object. Object is falling. Air resistance will be acting upward, opposing. Can you see that? So that causes the resultant force to decrease. When the resultant force decreases, the acceleration will also decrease. And at one point, I don't know which point, right? The speed of the object will eventually reaches maximum. And this is called terminal velocity. Air resistance balances the weight of the object. So when the air resistance is equal to the weight of the object, right, the resultant force is 0. So the object has 0 acceleration and the object will fall with terminal velocity. That is how we explain for 3 to 4 marks. Now, move on. Mass vs weight. Mass is being defined as the amount of the substance contained in your body. How many atoms inside your body? That will give you your mass. Right, okay. And bear this in mind. Units of mass would be kilogram or gram. And mass is constant no matter where you are. So whether you are on the surface of the earth, you are on the surface of the Jupiter, you are on the surface of the sun, oh my god, that's too hot, you are on the surface of the moon, your mass will never ever change because the amount of atoms in your body, right, is the same. What about weight? Weight, okay, let me highlight first. Mass, amount of substance contained in a body. Gravitational, weight is the gravitational force acting on the body. So weight is actually a force. So the unit of weight is Newton. Weight, okay, depends, okay, on gravitational acceleration, or we call it as gravitational field strength. So there is a relationship between mass and weight, okay? What's the relationship? W is equal to mg, right? W is weight, W. M is the mass. G is called gravitational acceleration. So I don't dare to put the value. If this is a gravitational acceleration on Earth, then it is definitely 9.8. But if it is a gravitational acceleration on the other planet or on the moon, then the value of G will be different. So can you see the weight depends on the value of G because the mass is constant. And if the weight is measured in Newton, you just bear this in mind, the mass must be converted to kilograms. So some of the students might, okay, make careless mistakes. So you bear this in mind, okay? So the G is meter per second square. That's the relationship between mass and weight. Memorize this. Now, density. The definition of density is as simple as mass per unit volume. Okay, formula, if you want to ask. Formula, rho is equal to m over v. M represents mass, rho represents density. So the units of density, units, could be gram per cm cube or kilogram per meter cube. And density is a scalar quantity. Because mass is a scalar and volume is a scalar as well. Now, paper 4. So sometimes paper 4, you need to discuss a simple experiment, how to calculate density of an irregular shaped object. Remember just now we discussed on how to measure the volume of the irregular shaped object? And I told you that the volume of the irregular shaped object can be calculated by the difference between the two volumes of the water in the measuring cylinder. This is almost similar, right? So first thing you do, okay, this question could give you 3 to 4 marks. So I would say, okay, measure the mass. Because density, you just write down. If you want it to be easier for you, not to miss any step, density is mass over volume. How do I measure the mass? Okay, so you have to write down the apparatus. Measure mass of object, I will just say object, by using electronic balance. Done. Second, okay, fill, same thing as how you measure the volume. Water into measuring cylinder. Take its initial volume. Third, carefully place irregular shape object or just object into measuring cylinder and take its final volume. And then volume of irregular shape object is equal to final volume minus initial volume. And last one, density can be calculated by mass of object. If you want to put a unit, yes, you can put gram, divided by volume of object or irregular shape object, which is in cm cube. Done. Right? I will highlight the keywords for you. Okay, another thing that you have to bear in mind is that the question would definitely mention that whether this object is a large object or small object. But if the question wants you to use the measuring cylinder to measure the volume of the irregular shape object, they would definitely mention that this is small irregular shape object. So don't worry about not fitting into the measuring cylinder. So measure mass using electronic balance. We want to see that. And then fill water, measuring cylinder. I want to see you take initial volume. And then place irregular shape object, place object into measuring cylinder. Take final volume. And then volume of irregular shape object, final volume minus initial volume. So density, mass over volume. That's all. Now, okay, I put a blank space here for me to write, but I have already written down there, right? Relationship between momentum and resultant force. First of all, the definition of the resultant force. You have to remember, resultant force is being defined as, okay, rate of change of momentum. Because I do see some of the students define resultant force or force as mass multiplies by acceleration. That is not true. Remember that. Erase that away right away. Right? Resultant force or force is being defined as the rate of change of momentum. I'll prove it to you. Rate means per time. Change of momentum means final momentum minus initial momentum and divided by time. See that? Final momentum is mv, initial momentum is mu. M represents the mass because momentum depends on mass. How to, okay, calculate momentum? Mass times velocity. That is how we calculate momentum. V represents final velocity. U represents initial velocity divided by time. So factorize out the m. This is F, yeah? Factorize out the m. Okay. V minus U over T. You see that? Now, V minus U over T, that is the definition of acceleration. Acceleration is being defined as the change in velocity. Final velocity minus initial velocity per time taken. That is why you modify it to become F equals to ma. Now, if you want the relationship between resultant force and rate, okay, and momentum, this is it. The ones that I highlight. Now, I'm further doing it so that you can see that how do we get F equals to ma. That's all. Next one, Hooke's law, right? So Hooke's law, yes, it is quite important in your paper 4. The definition, okay, or Hooke's law states that the extension is directly proportional to the force applied, but it has to occur beneath. Extension directly proportional to force, but beneath the limit of proportionality. Maybe you want to ask, what is the limit of proportionality? Let me further explain on that. Limit of proportionality is a point which being exceeded extension, give me a while, extension is no longer proportional to force. Highlight the keywords for you. A point being exceeded extension, no proportional to force. That is, okay, limit of proportionality. So Hooke's law, extension is directly proportional to force, or force is directly proportional to extension. So the equation, the graph, whenever you plot, force or extension could be in cm, could be in mm, could be in meter. So you have to start your graph. They will ask you to sketch, yeah? You have to start your graph from origin all the way, straight line graph. See that? So I told you before, when the graph is being given, you can find the area and the gradient, right? Gradient is equal to K, which is called spring constant. So since this is a straight line graph, whether you find the ratio or you find the gradient, you will end up getting the same answer, right? So the formula of Hooke's law, F equals Kx. F is called force, K is called spring constant, and X is called extension. Now I further explain on the area. Area of this force extension graph represents elastic potential energy. And I also want you to bear in mind, Hooke's law is only valid to elasticity. So in your syllabus, it is valid to spring, it is valid to rubber band. Okay, so area under the graph, which is area of triangle. Can you see that? Half Fx. That is why your elastic potential energy is half Fx. I highlight. Okay, but you know, sometimes, right, you can modify your equation. You can modify your formula. You know that F is equal to Kx. See, I modified. So your elastic potential energy can be, replace the F with Kx, so you get half Kx squared. So this is another equation for elastic potential energy. Two formula, half Fx and half Kx squared. And the formula of Hooke's law, F equals to Kx. Now, resultant force, right? Resultant force is being defined as the sum of all the forces which are acting on one object. For example, okay, I have this one object right here. I have, okay, 1 Newton and then 10 Newton. See that? To find the resultant force, first thing you do step by step is that you look at the directions of all the forces. This is towards left, this is towards right. And then you put one direction as positive. So I will put towards left positive because the magnitude is larger, towards right is negative. So the resultant force would be equal to -1 plus 10. So you get 9 Newton. That's how you do it. Okay, but if the forces are acting in perpendicular direction, so you have to use Pythagoras theorem. You draw your vector triangle first, right? Maybe you draw, okay, vector triangle like this. Tip to tail rule. Maybe this 6 Newton, this is 10, this is 8 Newton. Okay, then you calculate. Sorry, okay. Calculate the resultant force. So the resultant force, square root 6 square plus 8 square. So 36 plus 64. So you get square root of 100, which is equal to 10 Newton. That is how you do it to find your resultant force, okay? Now, centripetal force is also one of the resultant force that causes an object to travel in a circular path. Another thing about the centripetal force is that, bear this in mind, it acts perpendicularly to the direction of motion or the direction of the velocity of the object. And then it does not change the speed of object. It will never make object move slower or faster. Got it? And then causes object to move, okay, in circle. You see the word circle, you see the word curve, you see the word bend. This is centripetal force. And then the direction of the centripetal force, direction towards center of circle or bend or curve. Now, turning effect of a force, or we call it as moment. The definition of moment is the product of force and the perpendicular distance from the pivot. Right, for example, if you have, okay, let's say this is the pivot. Pivot is a turning point, right? So this is a pivot. Okay, or I call it as fulcrum. If there is a force acting, so you look at the direction of force first. If the force acting in vertical direction, whether downwards or upwards, it doesn't matter. So vertical direction. So you want to find the perpendicular distance. The perpendicular distance must be horizontal. This is called perpendicular distance. So to find the moment is equal to F times D. Done. And since I talk about the turning effect, right? So turning effect, it could occur in anti-clockwise or clockwise direction. So if you want to see whether it is clockwise or anti-clockwise direction, you look at the direction of force first. Force is going down. And then while force is going down, where the pivot is on the left-hand side of the force. Pivot is on the left-hand side, force going down while turning towards the pivot. Down, follow the direction of force and turn towards the pivot. So when the force turns in this direction, this is called clockwise direction. See that? If I have another force, for example, I have another force which is acting in upwards direction, like this. So you look at the direction of force first, going up, right? So where is the pivot? Pivot is on the left-hand side. So while going up, it will turn towards the pivot. This is called anti-clockwise direction. As simple as that. Now, principle of moment, right? Principle of moment is one of the conditions for the object to be in equilibrium. You know that, okay? For an object to be in equilibrium, total anti-clockwise moment must be equal to total clockwise moment. So you can form equation from that. So how you know that an object is in equilibrium? You look for the words like, okay, clue, okay? From the words like horizontal, balance, not moving, at rest, stationary. These are the clue words to indicate that the system is in equilibrium. Okay, so form an equation, total clockwise moment, check for all the clockwise moment you put on the left hand side is equal to total anti-clockwise moment put on the right hand side. That's all. Now, okay, in paper 4, if the question regarding moment is coming out, right, the first part they will ask you to state the conditions for object or the system to be in equilibrium. There are two conditions only. One is that resultant force acting on the object must be equal to 0. That also being said that, okay, that means the upward force must be balanced by the downward force. Forward force must be balanced by the backward force. You get me? Then only you know that the resultant force is equal to 0. But the resultant moment, you have to see, right? Resultant moment, pivot point here. Okay, anti-clockwise moment must be equal to clockwise moment. See that? Anti-clockwise moment must be equal to clockwise moment. Those are the two conditions for the object or the system to be in equilibrium. Now, center of mass vs center of gravity. Center of mass is being defined as a point which the whole mass is considered to act. Center of gravity is a point in which the whole weight, gravity is related to weight, is considered to act. So what's the difference between center of mass and center of gravity? Right, to tell you the truth is that they are different. Right, but the problem is that, okay, not the problem. In your syllabus, we assume that they are the same point. So center of mass is equal to center of gravity. Let us move to describe a simple experiment to demonstrate that there is no resultant moment on an object in equilibrium, right? So not an object, maybe, okay, on an object, is this also okay? So I draw a ruler first. I draw the experimental setup. Okay, this is my ruler. Okay, I will explain further later. So, and then this is my pivot. So this is 50 cm mark. And then maybe I hang a weight here, or I place a weight. Just place a weight. And then another one. Okay. Mass A, mass B, and then this is uniform. Why do I write uniform? Uniform meter rule. Why do I write it as uniform? Because uniform means the center of gravity of this meter rule is at 50 cm mark, at the center of the meter rule, right? So I call this as fulcrum, or you can call it as pivot. And mass A, mass B, I have already labeled. Okay, now when you describe an experiment, since you draw a diagram, just write down setup, apparatus, okay, as shown. Okay, slotted mass, okay, maybe mass A. I maybe put mass A, okay? Fulcrum, okay, is placed at 50 cm mark on, okay, meter rule. And then mass A is placed, okay, at a distance, anywhere that you like, on left, okay, left side of meter rule. Mass B, okay, is placed, okay, is shift, is move, okay, on the right side of meter rule until meter rule is horizontal. Horizontal means balance. Done. And then continue, yeah? Okay. Now, continue on that. I would say that, okay, resultant force, okay, is zero, okay, when, okay, the two forces on meter rule by mass A and mass B equals to force from pivot. But how do you check? Okay, so you want to check, measure the height on two sides, okay, of meter rule. I will draw on the diagram here. Okay, this is fulcrum. Okay, you measure this height from the ground. This is height 1, this is height 2. Okay, so if the two heights, if H1 is equal to H2, then resultant force is equal to 0. But moment, how do you do it? Okay, moment, anti-clockwise. Okay, then calculate mass A going downwards because the weight of A is going downwards towards the fulcrum. This is called anti-clockwise moment. Mass B going downwards because the weight of B is going downwards while turning towards the pivot. This is clockwise moment. So calculate anti-clockwise moment by mass A. Okay, how do you calculate? Okay, mass A in, shift myself up a bit, in kilogram multiplies by 9.8. Okay, and compare with clockwise moment by mass B. Mass B in kilogram, you have to convert to kilogram times 9.8. Okay, moment times the distance. Add this a bit, I forgot to add that, times distance A. I will put that. And, okay, times distance B. Okay, now this is what we call distance A from the pivot. And this is what we call distance B from the pivot. Okay, if anti-clockwise moment by A is equal to clockwise moment by B, resultant moment is equal to 0. Done. So moving on to momentum. The definition of momentum is mass multiplies by velocity, or the product of mass and velocity. So the formula of momentum, this is a simple momentum. P is equal to mv. M represents mass, V represents velocity, right? So the units of momentum can take kilogram meter per second because the unit of mass is kilogram. The unit of velocity is meter per second or Newton second. I will explain Newton second in the later slide. And momentum, just remember, it is a vector quantity. Even though the definition sounds easy, but when it comes into calculation, due to its nature of being vector quantity, some of the students might make careless mistake. You will see why. Now, impulse vs change in momentum. Impulse is being defined as product of force and time. Force multiplies by time. That is called impulse. And, okay, I want you to see, still remember when I define, okay, resultant force, how to relate the resultant force and momentum. Actually, there's connection between impulse and the change in momentum. Change in momentum is equal to final momentum, which is mv, minus initial momentum, which is mu. Right, V represents final velocity, U represents initial velocity. Change means the difference between the two momentums. Now, let us relate the resultant force to momentum first. Resultant force is being defined as rate of change of momentum, mv minus mu over t. So when you cross multiply the t, you times up the t, you get ft is equal to mv minus mu. So I want you to see this carefully. Ft, this is called impulse. mv minus mu, this is called a change in momentum. So in other words, you can also Okay, right, impulse is equal to the change in momentum. It's not a problem. Could you see the change in momentum share the same unit as momentum? So that is why, right, look at your impulse. Okay, look at your momentum. This is a unit of impulse, can be equal to the unit of momentum as well. Now, principle of conservation of momentum states that in a closed system, you don't like to use the word closed, you can use isolated system, right? The total momentum is conserved. That also being said that the total initial momentum equals total final momentum. So I'm going to highlight the key points. Closed system is a key point, one of the key points. Total initial momentum equals total final momentum. Let me further explain on closed system or isolated system. You see, momentum is about moving mass. As long as the mass is moving, the mass has momentum. Agree? But we are surrounded by so many invisible air particles. When you think of me, when I'm moving, so definitely there will be air resistance acting on me, right? Which causes my speed to change. Right. So if you want to use the principle of conservation of momentum, right, this principle of conservation of momentum, try to simplify the calculation. So we ignore the resistive forces that could occur. Like for example, trolley is moving. There will be air resistance, there will be drag forces, and there will be frictional forces acting on the moving trolley. So, right, not to make things more complicated, we call it as closed system because we want to ignore all the resistive forces like frictional force, air resistance, etc. So when you do, you use the principle of conservation of momentum, forget about the frictional forces, forget about the air resistance, right? So you just put total initial momentum equals total final momentum. As easy as that. Now, move on to work vs energy. Work is being defined as the product of force and distance that move in the direction of force. Sound confusing a bit? Okay, I will show you. This is the formula of work, right? Okay, W is equal to F times the distance. So you have to make sure that the distance and the force occur in the same direction. In other words, let's say there's an object in front of me. So if I want to do work on the object, I give an object. Okay, I give that object. I apply a force on the object, a gentle push, right? Pushing is a force. I push the object move forward in the direction of my force. If I push the object move backward, that is not the direction of my force. Do you get it? So whenever you solve the work question, you have to make sure that the force and the distance occur in the same direction. And then only you can safely multiply. Energy is being defined as ability to do work. Right, so in other words, okay, without the work, okay, without the ability to do work, you have no energy. So most of the time when you solve any questions related to energy and work, you can put energy is equivalent to work, or work is equivalent to energy. Some of the students ask, right, work and energy are both scalars. But some of the students ask, how come this is force? Force supposed to be vector and the distance move in the direction of force, okay? Or we call it as displacement supposed to be vector. How come work is a scalar? Okay, let me explain further on that. Yes, force is a vector because you push an object or you pull an object, right? And then the distance move in the direction, distance in a certain direction, that is called displacement. That is also a vector. But when you calculate the work, okay, before you calculate the work, you have to make sure that force and distance occur in the same direction, put a full stop to that, and then you just take their magnitudes. You just multiply their magnitude. That will give you your work. That is the reason why work is a scalar quantity, because we just look at the magnitude after we make sure that the two directions are in the same, the two physical quantities are occurring in the same directions. Now, important thing I need to tell you again because it appeared in one of the past year questions. Now, a distance must act in the same direction as force. Let me discuss one of the past year question here. A builder lifts one concrete block from the ground onto a platform. The weight of one block is 170 Newton. What is the useful work done against gravity on one block? Okay, how do you solve this kind of question? So if you want to solve this kind of question, you look for the clue from the information provided. This is a builder lifting one block, concrete block, from the ground onto the platform. The weight of one block is 170 Newton. So you are asked to find the useful work. So write down the formula of work. W is equal to force times the distance moved in the direction of force. Now I want you to see this. Weight. Weight is called the gravitational force. When you talk about one block, right? The weight of one block, let us look at this block. Okay, just one of these block is acting downwards. You see that? This is the weight of one block, which is 170 Newton. So there are two distances given. One is 2.6 meter, the other one is 2.1 meter. So which distance that you're supposed to use? So the distance that you're supposed to use is 2.1 because it occurs in the same direction. It occurs in the direction of plane of the force. Vertical direction, we call it. So that is why to find your work, you just take your force, 170 because useful work done against gravity on one block, right? Done against gravity. Gravity is acting vertical, in vertical direction. So that is why the distance must occur in the vertical direction or y-axis. So 2.1. So 170 times 2.1, that gives me 357. I round it off to 360 joules. Done. That is how you do it. The next one is called gravitational potential energy, or in short, GPE. Gravitational potential energy is being defined as the energy due to position of the object measured from the ground. So this is the equation or the formula. GPE is equal to mgh. M is the mass. Since the GPE must be measured in joules, the mass must be in kilogram. G is called gravitational acceleration. Gravitational acceleration. And the unit is, or the value is 9.8 meter per second squared, unless the question asks you to use 10. H is the height from ground. That also being said that when the object is on the ground, it has to be in meter. So that also being said that when the object is on the ground, the GPE of this object is equal to 0, unless you lift this object up from the ground. You give the object a certain height measured from the ground. So this is called the height measured from the ground, h. So GPE is equal to mgh. And the unit of GPE is in joules. Formula is not given. That is why you need to memorize the formula. Now, the next one is the kinetic energy. Kinetic energy is the energy due to motion. As long as the object is moving, object has kinetic energy. So the formula, Ke represents kinetic energy, which is half mv squared. M represents mass. Since this energy, all the energies, all the works must be measured in joules. That is why the mass must be converted to kilogram. V is called speed, but you have to square it. So it is meter per second squared. And the unit of kinetic energy is equal, the unit is joules. So memorize this, energy due to motion, the formula of the kinetic energy. Now, the next one is elastic potential energy. Remember when I talked about the Hooke's law? Right, I told you that Hooke's law, when the graph is being given, the graph of force against extension, the area under the graph represents elastic potential energy. So the definition of elastic potential energy is the energy, okay, due to, okay, the ability of an object to return to its original dimension. You can also replace the dimension with size, length, right? Once force is released. So you apply the force, right? You apply the force on the rubber band, you stretch the rubber band is getting longer. But before you stretch that, you have to measure the initial length of the rubber band first. So when you stretch it, the rubber band will get longer. So when you release your force, you try to measure, right, the final length of the rubber band. If the final length of the rubber band matches the initial length of the rubber band, that means that rubber band is elastic, and that rubber band has elastic potential energy. So the formula, there are two formula, half Fx and half Kx squared. So what is F? F is force. X is called extension. So the extension must be in meter, force must be in Newton for the elastic potential energy, or in short, EPE, to be measured in joules. K is called spring constant. Standard unit is Newton per meter. X is called extension, also measured in meter. So that is why these are the two equations for elastic potential energy. So the keyword energy, due to ability to return to its original dimension, force release or remove. Now, principle of conservation of energy states that energy cannot be created nor destroyed, but can change from one form to the other form. In order for you to use the principle of conservation of energy, right, you have to consider two situations. First, second. The first situation is whether the resistive forces are ignored. If the resistive forces are ignored, okay, you can write your principle of conservation of energy as total initial energy equals total final energy. But you have to determine your initial and your final energy. That's all. But if the resistive, second situation is the resistive forces are not being ignored. So if the resistive forces are not being ignored, this is how you write your equation for the principle of conservation of energy. So your total initial energy could be more than one. So you just find the total minus the energy dissipated to overcome, dissipated to overcome resistive forces equals total final energy. That also being said that your total initial energy is always larger than your total final energy. So why? Because some of the initial energy is used to overcome the heat or heat loss to the surrounding, or the resistive forces like frictional force, air resistance, drag force, etc. Now, efficiency. Okay, efficiency is just to see, right, how much energy that I provided to a certain stuff, like maybe motor, and this motor can convert to the useful energy or useful output power. So how much energy is not being wasted? How much energy is being converted to useful energy? That is called efficiency. There are three formulas for efficiency. The first one is efficiency is equal to useful output energy divided by input energy multiplies by 100%. If you only want to find a ratio, not multiplying with 100%, that is okay, not a problem. Now, second equation, efficiency is equal to useful output power divided by input power multiplies by 100%. And the third formula, efficiency could also equal to useful output work divided by input work multiplies by 100%. So it depends on the question. Power. Okay, power is being defined as work done per unit time taken or the energy per unit time taken. So this is the equation formula of power. Power is equal to W over T. Power is equal to energy over time. It depends on what kind of energy. Could be kinetic energy, could be gravitational potential energy. Right. Now the unit of power, the units of power could be in watt, W-A-T-T, capital W, or joule per second. And power is a scalar quantity. So these are the two formulas. Memorize this. Now, pressure, the definition of pressure is force per unit surface area. All the formula, P is equal to F over A. A represents the surface area and F represents the force. Right, the units of pressure could be Pascal, right? Could be Newton per cm square, Newton per mm square. And pressure is a scalar quantity. So this formula of pressure is normally used to find the pressure of solid. Right. Now, another thing that I should remind you is that, okay, bear this in mind. 1 Pascal is equal to 1 Newton per meter square. Remember that. So when you see Newton per meter square, that is equal to 1 Pascal. Because the force must be measured in Newton and the area, the standard unit of area is meter square. So Newton per meter square is equivalent to Pascal. So due to pressure is also related to some other physical quantities like pressure acts in all directions, right? Pressure increases with depth. Pressure depends on density, right? So we can derive a pressure for fluids. Fluids are gas and liquid. So for pressure of fluid, P is equal to rho GH. Rho is the density of the fluid. G is the gravitational acceleration. H is the depth or the height measured from the ground. The depth of the liquid, let's say this is a liquid, the depth of the liquid must be measured from the surface of the liquid. This is where we measure the depth, H, for liquid. And rho is the density of the liquid. G is the gravitational acceleration, which is 9.8 meter per second square, unless the question asks you to use 10. So in this slide, what is important here, the definition of pressure, force per unit surface area, as well as the pressure of fluid. Now, states of matter. I know you learned about, many states of matter. It is not just 3, more than 3 actually. But in your syllabus, the good news is that we only focus on 3 states of matter: solid, liquid, and gas, right? So what about solids? Okay, you need to understand solid, the atoms are well arranged or closely arranged, right? So solid particles cannot move. Atoms can only vibrate at their fixed position. Don't just state that atom can only vibrate. Vibrate at fixed position. That means, right? So this is a fixed position of the atom, which is when the atom is not moving, right? When the atom is moving, atom can move up and down, okay? At mean position, fixed position is called mean position, up, down, or left, right. That is called vibration. Liquid, on the other hand, okay, particles are further apart, okay, as compared to solid. Particles can move but restricted, okay, can move but restricted. Or you can also say that particles can slide past each other. They can move, but not as they can move freely, not so free, but as compared to solid, they can move a little bit. Gas, on the other hand, particles are very far apart. Okay, and they move in random, use the keyword like random directions all the time. So I'm going to highlight the keywords first. Well arranged, vibrate at mean position or fixed position, right? Particle further apart as compared, you have to compare to solid. So can move but restricted. Gas particles are very far apart. They move in random directions. We want to see that. Now, okay, I remember one of the past year questions stated that why gas is easily compressed as compared to liquid. So if you want to write about why the gas is easily compressed, you need to talk about this force. Have you ever heard about this force? Intermolecular forces. Intermolecular forces means the forces between the particles inside that solid, inside that liquid, inside the gas. Since the gas particles are far apart from each other, so the forces between them, the intermolecular forces of the forces of attraction between the gas particles are very, very weak. So that is why we can apply external force to compress the gas. So that is also one of the reasons why the gas is easily compressed as compared to liquid. Closer the distance, stronger the intermolecular forces. So solid has the strongest intermolecular forces. That is why it is not easy to change the shape of the solid. Because the particles are arranged in a very close manner, right? They attract each other, and the force, the intermolecular forces between them is super duper large as compared to gas. Now, absolute zero is being defined as the minimum, okay? Minimum or the lowest temperature, okay? Or the lowest temperature which particles can possess. So if I put, okay, if I put zero temperature, it is not possible because we are surrounded by so many objects. So it is not possible to get exactly zero. So the value is 0 Kelvin or negative 273 degrees Celsius. And one more thing, you need to know how to convert degrees Celsius to Kelvin or Kelvin to degrees Celsius. If you want to convert Kelvin to degrees Celsius, remember, all you need to do, you just minus 273. If you want to convert degrees Celsius to Kelvin, all you need to do is that you have to add 273. That's all. Now, how gas exert pressure? Have you ever seen this type of question before when you answer a lot of past year questions? Yes, this type of question is quite popular, and the marks given is 3 marks. First of all, you have to talk about how the gas particles are moving. Gas particle exert pressure, that means the question needs to tell you that the gas is inside a container, right? Or inside a box or inside, okay, just a container. Right, now we need to talk about the gas particles are moving in random. I will highlight the keywords later. Directions. Okay, and they collide with themselves and wall of container all the time. And the collision are elastic. What do I mean by elastic collision? Meaning to say that when the gas particles is colliding with themselves, they don't stick to each other, they bounce. Okay, they must be separated, or they collide with the wall of the container, so they bounce off. They cannot stick to the wall. That is called elastic collision. And due to elastic collision, okay, there is change in momentum. Final momentum minus initial momentum, right? Due to the change in momentum, remember, rate of change of momentum is force. So pressure equals to force exerted by gas particles on wall of container per surface area of container. That's it. So I'm going to highlight the keywords for you. Gas particles are moving in random direction. Want to see this? Collide with themselves and wall of the container. Whether you like collisions are elastic or not elastic, okay, it doesn't matter if you don't write the collisions are elastic. So due to the collision, there is change in momentum. So rate of change of momentum is your force, pressure, just write down the formula of pressure. Force divided by surface area of the container. So it is enough if you want to write pressure is equal to force over surface area, because you have already explained how the force is being exerted on the wall of the container due to the collision of the gas particles with the wall of the container and rebounds off. Now, pressure vs volume at constant temperature. Now, let me give you one example. You know, I used to play prank on my friend, my classmates. We have a can of Coca-Cola, remember? And then we just shake it, shake it, shake it, and keep on shaking, shaking, shaking. And we acted like we are so kind. And I tell my friend, oh, you can have this Coca-Cola can. And when my friend opened the can, you know what happened next, right? So that is related to Coca-Cola as well, right? Pressure vs volume. Let me explain in terms of Coca-Cola first. How about that? Right, you see this is a Coca-Cola. This is a can. Okay, this is a can. And then inside this is Coca-Cola. Definitely it's not full, right? So when you shake it, right? So Coca-Cola produces gas bubbles, the bubbles, okay? And then when you shake it even more bubbles are being produced and less space for this bubble. So that is why when your friend opened the can, right? You know what happened next, right? So now I would like to explain what happens when the pressure, okay, when the volume, how the volume affect the pressure when the temperature is constant, right? Okay, I'm going to write it down. When volume increases, distance between particles increases. So when the distance between particles increases, all the particles are moving away, right? What happened? Less collision, because these are gas particles inside a container. So when you put the gas particles inside a big container, so less collision between themselves and wall of container. When less collision, okay, less force, or you just say less change, okay, smaller change in, okay, rate of change Okay, I would say the rate of change of momentum decreases. How about that? Okay, rate of change of momentum decreases. Can you see that? Okay, force decreases. I write down the formula for you to see. P is equal to F over A. Surface area of the container is the same. Because it is the same container, we just increase the volume. It's just like a string. You see, this is a string. Okay, this is where you put the piston. So this is the area of the piston. It's the same. It's just that when I increase the volume, I increase the length. I'm increasing the volume. I increase more space, right? So that is why pressure is directly proportional to force. Hence, pressure decreases. Okay? Now, when the volume decreases, see what happened? When the volume decreases, that means I push this piston towards left to decrease the space between the particles. So the distance between the particles will also decrease. So when you have the same number of the particles inside the piston, right? Inside the container, so more collision because they have nowhere to go. So more collisions between themselves and the wall of the container. So the rate of change of momentum will have to increase and the force increases. And that is why the pressure increases. That is how you're supposed to explain. Now let us look at pressure vs temperature at constant volume. You know temperature, remember, temperature is affecting the kinetic energy. So when the temperature and kinetic energy cannot be separated, temperature is proportional to the kinetic energy. So I'm going to write that down. When temperature increases, right, kinetic energy of particles increases. So particles move faster and collide with themselves and wall of container more frequent. So, okay, larger change in momentum, rate of change of momentum increases. Increases force, okay, exerted increases, hence pressure increases when the temperature increases. You see what happens? Right, now when the temperature decreases, this is how you explain. Kinetic energy of the particles will also decrease. So the particles move slower and collide with themselves and wall container less frequent. So smaller change in momentum, rate of change of momentum decreases. Force exerted is also decreases. Hence, the pressure will have to decrease when the temperature is decreasing. You just replace the words increase, decrease. Now, momentum vs pressure of the gas. So start from momentum. How the momentum affect the pressure of the gas? Let me explain. Now, this is a container. So I'm focusing on one particular gas molecule, right? Gas particle, how about that? So this particle move towards the wall with an initial speed of u. This mass of the particle is m. So collision is elastic. This particle, the same particle, will rebound back with the same speed. See that? And it is the same particle. So when you want to find a change in momentum, still remember how we find it? It is the final momentum minus initial momentum. And before you do that, you have to bear this in mind. Momentum is a vector quantity. And I want you to take a closer look to my diagram. Could you see the direction of the initial velocity is towards the wall? And the direction of final velocity is away from the wall of the container. So it is very important for you to mark directions for momentum. So I would take direction away from the wall as positive, direction towards the wall as negative. So my change in momentum will be m positive u, final velocity, minus m negative u. Initial velocity has to take negative direction. So mu minus m negative u, negative mu. Could you see? Negative and negative becomes positive. So 2mu is the answer. 2mu is the change in momentum. So due to the elastic collision, right, that would be a change in momentum. So larger change in momentum, right, because of force, you see pressure is equal to force over area. And the force is equal to, if you cannot remember, it is okay. You can still use MA. MA, no problem, no problem. Okay, if you want to use MA, you want to derive it back, it is okay. You know the definition of acceleration. It is final velocity minus initial velocity per time taken. Sub into this equation, you have mv minus u over t. Multiplies in your mv minus mu over t. See that? That is your force. Sub into pressure. So the pressure is equal to mv minus mu over T times the surface area. See that? So that is why larger change in rate of change of momentum, larger pressure. See that? Or you just want to say, okay, larger change in momentum, no problem with that. Larger change in momentum, larger pressure. Could you see? Smaller change in momentum, smaller pressure. You can use equation when you explain the physical quantities. But you have to explain every symbol that you are using. That's all. Now, move on to conduction, convection, and radiation. This is how the energy, the heat is being transferred, right? The process of conduction, right? It is the transfer of heat from hotter end to the colder end occur in solid. And bear this in mind, for conduction, there must be physical contact between the two solid. So that means, right, I have a rod here. Let's say this is a copper rod. I set up fire and my hand is holding the other end of the copper rod. So when I set up fire, you know, heat transfer from the hot particles through collisions with other atoms inside the copper, and by the delocalized free electrons that transfer the heat very quickly to the other end of this rod, my hand will feel very hot. So that is what I meant by physical contact. Right, convection, right, on the other hand, it is the circulation of heat from the hotter region to the colder region. And convection can only occur in fluids. Do you know why? Because solid particles cannot move. Fluid particles can move up, down, up, down. Okay, now radiation is the transfer of heat from the hot region to the colder region without physical contact. I give you one example. Right. Every morning, you look at the sunrise. Okay, you can feel the heat from the sun. But between the sun and the earth, because we are on the earth, you can't, between the sun and the earth, there's nothing. It is just vacuum. But still, we can feel the heat from the sun. That is called radiation. Right? There's no physical contact between the sun and the earth. when you go for maybe you attend a camp, okay, camping. So nighttime, all these campers, they set up campfire, and all the campers will sit, okay, close to the fire, right, close to the flame. You're not touching the flame, but you can feel the heat from the flame, so you feel more comfortable, not that cold during the nighttime. That is also called radiation. Okay. Now, let me explain a little bit on the process of convection. Let me draw something, right, to explain the process of convection, circulation of heat, to make you understand better. Okay, this is a container, and then I fill in water. So this is where I supply heat to one side of the container. This is heat. I want you to look at the particles here, the water molecules here. The water molecules that are closer, right, to where the heat is being supplied will absorb the heat first. When they absorb the heat, they gain energy, they gain kinetic energy, right? So when they gain kinetic energy, they can move further away from each other. So when they move further away, the distance between the liquid molecules here would be larger. When the distance between the liquid molecules are larger, we said that the volume increases. The volume of these liquid molecules increases. When the volume of the liquid molecule increases, look at density. Density is equal to mass over volume. Volume increases, density will be lower. So these molecules over here will be less dense. When they are less dense, they need to go upwards. They cannot sink. Denser materials sink. Right, so they leave behind some free spaces here. So these free spaces here will be immediately replaced by the water molecules, which are not so hot, right? Because the distance between the water molecules that are not so hot, because they have lesser kinetic energy. So the distance between water molecules, colder water molecules, are closer, so their volume is actually lesser, so that is why their density is denser, so circulation of heat occur. That is process of convection. Hot air, hot water molecules, or hot liquid molecule rises. Remember this. Hot molecules, whether we are talking about air or liquid, rises. Okay, why? Volume increases, which makes them to be less colder cold molecules, okay, move down. Why? Because their volume, okay, is lesser. Volume are lesser. Okay, they are denser. Remember that. Now, the next one, boiling vs evaporation. Normally in paper 4, they ask you to differentiate between boiling and evaporation. What is the similarities between boiling and evaporation, and what are the differences between boiling and evaporation? Let me define them first. Boiling is the changing of phase from liquid to gas at constant temperature or fixed temperature. That fixed temperature is called boiling point. Evaporation, on the other hand, is the changing of phase. Same thing, changing of phase from liquid to gas, but at any temperature to gas. At any temperatures. That is the definition of boiling and evaporation. Now, let us look at the similarities. Similarity between, I put more than one, similarities between boiling and evaporation. And evaporation. Okay, the first one is both absorb heat and then changing of phase from liquid to gas. Difference, okay? Differences between between boiling and evaporation. So I draw a table, easier. This is boiling. This is evaporation. So first one, boiling occurs at fixed temperature, constant temperature. We call it as boiling point. Evaporation occurs at any temperatures. And then boiling occurs throughout the liquid. Evaporation occurs at the surface of liquid. Those are the differences and the similarities between boiling and evaporation. Now, the next one, how evaporation causes cooling effect. Right. Okay. You know that evaporation. I explain first. Okay. Have you ever Have you ever been to the beach before? Yes, right. Okay. Now let me explain. This is a hot sun shining down on the surface of the water. So the water molecules at the surface absorb the heat from the sun. Don't you think so? So they have higher kinetic energy. Their temperature is definitely higher because they absorb the heat as compared to water molecules deep down in the water. Kinetic energy is lesser. The temperature is also lesser. So these water molecules at the surface absorb the heat and some of them will vibrate and then they will move. Not vibrate, but they will move even faster, more vigorously, depending on how much kinetic energy that they have, depending on how much heat that they absorb. So some of the water molecules are able to break free the bonding between them and escape to the surrounding as gas state. But once they escape, don't bother about them. So the main thing is that they leave behind all these vacancies, all these free spaces. So all these free spaces will be immediately filled by water molecule which are not so hot, right? With lesser kinetic energy. Hence, the temperature decreases. Because the most energetic water molecules have already left, okay, the surface of the water. So that is why the temperature decreases. Okay, let me explain. Heat absorbed by water molecules at the surface, okay, which causes their temperature to increase. They have higher kinetic energy, okay, and then they move further apart from each other. Some of them are able to break free. Some of the energetic, some of the most, or some of the energetic. Energetic means the molecules with higher kinetic energy are able to break free and escape to surrounding, leaving behind water molecules of lower kinetic energy. Since kinetic energy is proportional, don't write directly proportional because they are not directly proportional. They are proportional to temperature lower kinetic energy results lower temperature. That is where the cooling coming from. Now I highlight the keywords for you. The keywords are heat absorbed first by the water molecules at the surface. We want to see that. So their temperature increase, higher kinetic energy. So some of the energetic water molecules, energetic water molecule are able to break free and escape to the surrounding, right? Escape to the surrounding, leaving behind water molecules of lower kinetic energy. And since kinetic energy related to temperature, lower kinetic energy results lower temperature. That is what we expected you to write. Now, color of the surface vs heat or radiation. You know, black is the best absorber of heat, and at the same time, it is the best emit of heat. Why? Because it can absorb a lot of heat. That is why it can release a lot of heat. Silver, okay, is the worst absorber of heat, and it is the best reflector of heat. Matte, okay, or dull color, it is the good absorber of heat. Shiny is a good reflector of heat. That's all that you have to remember. We move on to specific heat capacity. The definition of specific heat capacity is the heat supplied per unit mass. Highlight first, heat supplied per unit mass of a substance to increase the temperature by 1 Kelvin, or you can replace with 1 degree Celsius, not a problem. So the formula, I always write this. E is equal to mc delta T. This E represents heat or thermal energy, must be measured in joules. Mass is M, which is in kilogram. C is called specific heat capacity. And delta T means the change in temperature. Could be in degrees Celsius, could be in Kelvin. So the unit of specific heat capacity, units, yeah? Could be joule per kilogram per degree Celsius, or joules per gram per degree Celsius, or joule per kilogram per Kelvin, or joule per kilogram per gram per Kelvin. Joule per gram per Kelvin is rarely seen. Okay, and one more thing that you have to bear in mind, this is energy. Heat is a kind of energy as well. Sometimes, right, in our physics lab, we do not have Bunsen burner because we do not have the gas supply. So that is why we use heater. Our heater comes with heater rating. So the power of the heater is already stated on the heater itself. So you have to relate the power and the energy. Remember, power is equal to energy divided by time. It is the same thing. So where energy cannot be measured, so energy can only be calculated. So if you want to calculate your energy with power and time given, E is equal to power times time. Remember that. And the time must be in second, because the energy must be in joules, power must be in watt. So that also means that the time must be in second. This is in joules, this is in watt. That's all that you have to remember about specific heat capacity. Now let us move on to waves, right? There are two general waves, can be separated, divided into two general waves. One is called transverse wave. The other one is called longitudinal wave. So what's the difference between transverse and longitudinal wave? In paper 4, the definition of the transverse and longitudinal waves are equally important, and the examples of the transverse wave and longitudinal wave are also very important. So let me highlight the important key points for you to see. Wave is a vibration or oscillation from a mean or fixed position, right? So that is why transverse wave is being defined as vibration of particles that is perpendicular to the direction of travel of wave or the direction of propagation of the wave. So longitudinal wave, on the other hand, is being defined as a vibration of the particles which is parallel to the direction of travel of the wave. Now you can actually replace this word perpendicular with 90 degrees or right angle. And you can replace this parallel with along. Vibration of the particles is along the direction of travel of the wave. That's longitudinal wave, right? The examples of the transverse wave are examples of the transverse waves. It is a water wave, light wave, radio wave, microwave, etc. Now, for a longitudinal wave, I don't really memorize the examples of the transverse wave because there are so many transverse waves around us. So I only memorize the example of the longitudinal wave. Longitudinal wave is super duper example. There's only one example, which is sound wave. Anything related to sound, that is transverse wave. So when you see sound wave, you definitely know that this is longitudinal wave. It has nothing to do with transverse wave. Any other waves, except for sound waves, are all transverse wave. And I teach you another method to memorize the definition of transverse wave, right? This is how I memorize. You see the word trans, T, the word trans. Sometimes I myself, I get confused. So I write this down. Now, in the examination hall with so much of the pressures, right? So you just write this T down and then put 90 degrees. Oh, I know that is 90 degrees or right angle, or it is called perpendicular. Right, longitudinal wave, long. Could you see that? That is how I remember. Now, there are two types of waves graphs. One, I want you to see that the y-axis is always about displacement. What is the use of the y-axis? From y-axis, you can actually find amplitude. So amplitude is determined from y-axis here. This is called amplitude. And remember what I told you, that amplitude is a scalar quantity that cannot take a vector, cannot take a negative value, because this part will be negative. Let's say this is 10. For example, 10 cm, this will be negative 10. You just ignore the negative. That will give you the amplitude. Now, the main thing about the graph is that the x-axis. The x-axis could be different. So when you see that the x-axis is related to time, right? One complete oscillation is equal to one period. One complete oscillation is equal to one period, the time taken for one complete oscillation. That is how you determine period and amplitude from displacement time graph. So once you have already determined your period, you can actually calculate your frequencies. Do you remember the relationship between the frequency and period? Frequency is equal to 1 divided by period. That is how we calculate the frequency of this wave. Now, another graph is about displacement against distance. Now, displacement, when you see this is a displacement, bear this in mind, you can determine amplitude. In this case, amplitude is 10 cm. So even though this is a negative 10, just ignore the negative sign and you will get your amplitude. Now, the main thing about this graph is, could you see that the x-axis has been changed to distance? Right, when you see the x-axis is distance, bear this in mind, one complete oscillation, okay? The distance taken for one complete oscillation, that is wavelength, or we call it as lambda. So when you see the x-axis is distance, you can determine wavelength from this graph and no period. Now, due to that, we can form a general equation of the wave, which is V is equal to F lambda. What is V? V is called waves speed. F is called frequency. Frequency can only be calculated when the graph is being given. So the x-axis of the graph must be time. So that you can determine the period from the graph and you calculate your frequency based on frequency is equal to 1 over period. And lambda, the graph will be given as well, but the x-axis has to be distance. This is called wave length. So the unit of wave speed could be cm per second, meter per second. So it all depends on the wavelength. It all depends on the x-axis of the displacement time graph. That's all. Now, let us look at the waves phenomenon, right? The first phenomenon is called reflection. Reflection means, okay, every morning you wake up, you look at the mirror, you see your own reflection. That is called reflection. So what is the meaning of reflection? It means that there is a change in the direction of the propagation of the wave, the direction of the wave when the wave strikes a reflecting surface. To cause a reflection to occur, a reflecting surface must be exist. So you have to prepare a reflecting surface. Let's say this is my reflecting surface. Could be mirror, right? Reflecting surface. And bear this in mind, this line is super duper important. What is this line represents? A line, a dotted line, which is perpendicular to the reflecting surface. This line is called normal. Normal line, let me define, is an imaginary line which acts perpendicular to reflecting surface. That is called normal. Now, okay, look at our ray here, right here. Now, this ray going towards, okay, let me, draw first before I explain. The ray that is going towards the reflecting surface is called incident, incident wave. The wave that is directed towards the reflecting surface, that is called incident wave. And the angle between the incident wave and normal is called incident angle. Now, the wave that is going away from the reflecting surface, that is being called reflected wave. And the angle between the reflected wave and normal is called reflected angle. And there's also one rule of reflection which you have to remember. The rule, law, we call it law of reflection. Okay, states that angle of incidence, which is I, must be equal to angle of reflection, which is R. So if this is 40 degrees, R has to be 40 degrees as well. And normal is super duper important because the angle is measured based on normal and the wave, whether we are talking about incident wave or reflected wave. Now that is all about that. Reflection. Now we move to refraction. So the keywords for refraction is bending of wave. Wave can only bend when the wave travels through different media, maybe from air to water, from glass to air. Right, why wave ever bend? You have to remember that, okay? Due to the different densities of the different media. Of course, the density of the air is totally different from the density of the water. Right, due to the different density, the wave speed would change. So wave will have to travel slower in water, so that causes bending. Okay, now let me explain on refraction a little bit. Now, these are the things that you have to memorize. I am going to draw the different media. These are the two different media right here. One is this and the other one is this one. Okay, this is my normal. Still remember, whenever we draw and we measure the angle of incident or angle of reflection, normal is needed. And then I'm going to draw my incident wave and refracted wave. Refracted wave. Now this is it. Okay, I want you to see carefully. Okay. Now I draw my arrow so that you know where is my wave traveling to. So this is air. Let's say this is water. Air and water. So this is called my angle of incident. This is called my angle of refraction. If that's bending, the R is representing angle of refraction. This is the angle of incident and this is the angle of refraction. Angle of refraction must be measured from normal, between normal and the refracted ray. So I want you to remember one thing right here is that when the wave, okay, air is less dense. Air is less dense than water. Bear this in mind. When wave travels from less dense medium to denser medium, which is water in this case, wave is refracted towards normal. So that also being said that the angle of incident is larger than the angle of refraction. Okay? Now, when wave travels from denser medium, in this case is water, denser medium to less dense medium, wave is refracted or bent, refracted away from normal. That also being said that the angle of incident is lesser than the angle of refraction. Yeah, feel free to pause if you face any problem. If you want to copy, feel free to pause. Now move on. Now, refractive index. You know why we need a refractive index? This is not really a formula. This is a symbol of refractive index, small letter n here. Refractive index is we just want to see how much wave is being bent. How much bending has occurred. That is why we calculate the refractive index. Right, refractive index can be calculated because it is just a ratio. Sine incident angle over sine refracted angle. This is only true when the wave travels from less dense medium to denser medium. And refractive index can also be calculated by sine R refracted angle over sine I. This is only true when the wave travels from denser medium to less dense medium. And refractive index can also be calculated by speed of light in air over speed of light, because light is one of the waves in medium. Speed of light in air is given 3 times 10 to the power of 8 meter per second. That is the speed of light in air. And the last one, if you want to calculate the refractive index that occur inside the water, you can also calculate refractive index equal to the real depth of the water divided by apparent depth. Let me explain a little bit on apparent depth. You know, whenever you stand in the swimming pool, maybe the person outside of the swimming pool will look at you and it seems like your legs are getting shorter. That is due to apparent depth. So due to the refractive or due to the process of refraction, right, your legs seems to be shorter. Right, these are all the relationship between refractive index and other physical quantity. Now, don't be confused because you have to remember one thing. I give you one important tip. I did memorize this as well. I have a lot of formula to memorize, and I totally understand that you have so many equations, so many formula to memorize, right? I give you one important tip. How about that? Right? There must be a way, right? In scoring your physics, it's not always about memorization because this is no history. What do you think? Right? The best way to memorize this, which I use this until today, right now, this moment, and the value of the refractive index in your IGCSE physics is always more or equal to 1. So when you get a value of the refractive index, which is smaller than 1, you definitely know that something is wrong right there. So I have to, because if you calculate, you definitely have to formula, I mean, two values, right? Either you're talking about the angle of incident, angle of diffraction. These are the two angles that most of the students confuse, even valid to me. I confuse as well. So, but I know one clue is that whatever angle that I use, when I divide that two angles, sine two angles, and I get a value which is smaller than 1, I definitely know that there's something wrong with my calculation. So what I do? I just erase and I invert back. Let me give you one example. How about that? So we move back to this question. It's okay. I'll just draw it. Let's say this is still water, this is still air. So, okay, the wave travel from the water to air. And let's say this is maybe 30 degrees and this is maybe 70 degrees. So you maybe you confused or maybe you couldn't recall, right? You just know, hey, is it sine I over sine R to find my refractive index or sine R over sine I to find my refractive index? No worries about that. So you just use n is equal to, let's say, I use sine I over sine R. This is the most popular a ratio for the refractive index. So I use sine incident angle. So I know this is an incident angle, sine 30 divided by sine 70. Okay, get my calculator. Sine 30 divided by sine 70. Oh, I got 0.53. This is smaller than 1. I know that this is something wrong with my calculation. All I need to do erase, erase, and erase. Oh, I cannot get smaller than 1. It has to be sine 70 over sine 30. Let me do it again. Sine 70 divided by sine 30. And I got 1.88. That is the correct value. Right, which is more than 1. I know that. I'm correct. Right, that is in my refractive index has no unit. It is just a ratio. Now let me move on. Diffraction. Diffraction is the spreading of wave when a wave travels through a small aperture, a gap. One gap. That is called diffraction. And I want you to bear this in mind. When diffraction occur, no change in wavelength, no change in frequency of the wave, and no change in wave's speed. But there is a change, okay? There is a change in waves direction. So, due to spreading after passing through the small gap of the aperture, the waves is moving in all directions. We call that as changing in waves direction. That is due to, okay, That causes the velocity of wave changes. Because velocity is a vector quantity, not just depends on the magnitude, but also directions. Now, let me draw diffraction. Drawing diffraction, okay, they will give you a gap, small gap, okay, small gap, and the other one is bigger gap, maybe. Okay, when they give you a small gap and a big gap, and they give you this wavefront, these are the wave. Okay, okay, and okay. Normally they would draw three, same wave. Okay, and okay. And they will show you, oh, this is the direction of the wave going towards the gap. And the best diffraction could be observed when the wavelength, this is what I call wavelength. When the wavelength, the distance between one wavefront to the other wavefront is called wavelength. When the wavelength is similar to the size of the gap, maximum diffraction will occur. Right, so diffraction is the spreading of wave when a wave is being pushed into a small hole. Just remember when everyone, right, there's so many people wanted to get out from somewhere and you keep on pushing each other, what will happen? Okay, you show like a pushing. Once you get out, right, you spread in all directions. So make sure wavelength has no change, draw almost similar wavelength. But the wave becomes circular, a little bit circular. So this is called wavelength. And don't just stop right there because you need to draw the direction here. Spreading, that means spread, go in all directions. That is why I say the wave's direction is changing. Right? And then for a large gap, this is a small gap. For a big gap or large gap, just bear this in mind, no change in wavelength, only a little bit curve at the two ends of the wave. And then just a little bit curve like this, not circular at all, it's still a straight wave. And then don't just stop right there, just draw arrows, spread in all directions. That is how we draw diffraction. And move on. Now, critical angle vs total internal reflection. Let me highlight the keywords at the same time explaining this. Critical angle is actually the angle of incidence, right? When the light, or normally we use light ray, when the wave travels from the denser medium to the less dense medium, that causes the ray or the wave to be refracted at 90 degrees. That is called critical angle, the angle of incidence that causes the wave to be refracted at 90 degrees or between the two surfaces, interface of the two waves. But the wave must travel from denser medium to less dense medium. Total internal reflection is a phenomenon which causes all the light ray to be reflected into a denser medium when the light ray travels from denser medium to less dense medium. That is all. Now, there are two conditions in order for the total internal reflection to occur. One is the light ray has to travel from the denser medium to less dense medium. Second, the angle of incidence must be larger than the critical angle of that particular medium. Right. Now, let me explain a little bit, okay, on the simple experiment on total internal reflection. And at the same time, I could explain critical angle, make you understand more. So I'm going to describe a simple experiment. I write down the title first. Describe a simple experiment for total internal reflection of light. I am going to draw while explaining. So there are three situations that I would like to draw here. Normal is a mass. Okay, and this is maybe water. This is air. Still water. This is air. This is air. This is water. Okay, I use the laser box inside the water because the laser box will give out more illumination, brighter light, so that my experiment result will be more accurate. I can view, okay, clearer. So this is my laser box, okay, and then I emit light, okay. This is the angle of incident. I start from the small angle. So you know when the angle of incident, this is from water is denser as compared to air. So when the angle of incident is smaller, let's say this is angle of, because I don't know the angle of critical angle of water. So if the angle of incident is smaller than the critical angle, C represents the symbol of critical angle. So if the angle of incident is smaller than the critical angle, you could see this. Some of the light will be refracted. Some of the faint ray will be reflected. You could see two rays actually. But when you keep on increasing, keep on moving your laser box, okay, until one point your angle of incident equals to your critical angle. This is what happenings, right? The light ray will be on the surface of the water. It's so beautiful. Right, you shall try this experiment in the lab. It's very beautiful. And the last one, when you keep on increasing the angle of incident to be larger than the critical angle, this is how I know. When I see that the light has already formed a horizontal ray on the surface of the water, I know, oh, that is the critical angle of the water. That is how I measure the critical angle of the water by using simple experiment. But when I keep on increasing the angle of incident, which I causes it to be larger than the critical angle, this is what happening. All my light ray will be reflected into the denser medium. In this case, it's water. Now let me explain. When light ray must be directed from water. Okay, light ray must be directed from water, which is denser medium, okay, towards air. So when angle of incident is smaller than the critical angle, some of the light rays are refracted towards the air or away from normal, some are reflected into water. And then when angle of incidence is equal to the critical angle, all the rays are refracted at 90 degrees. And then when the angle of incident, which is larger than the critical angle, all the rays are refracted into denser medium. In this case, it is water. That is how you're supposed to explain, but that is how you're supposed to describe a simple experiment. Let me highlight the key points. Light ray, okay, must be directed from denser medium. And then angle of incident is smaller. You could see that some of the rays refracted, we want to see that word, and some of the ray reflected into the water. Angle of incident is equal to the critical angle, ray refracted at 90 degrees. Angle of incident is larger than the critical angle, all the rays refracted, not refracted, I'm so sorry, reflected reflected into denser medium. Also, we call this as total internal reflection occurs. Reflected. That's all. Now, refractive index. Okay, so when the question told you that, okay, you see these keywords like, okay, light, ray, or the wave, okay, refracted, refracted. At right angles, or you say 90 degrees. You see all these keywords. These are all the keywords, 90 degrees, or refracted at the interface between two medium, right? You can actually modify your refractive index. N is equal to 1 over sine C. C is called critical angle. So when a critical angle is being given, okay, you know that, see this word, right angle, 90 degrees, interface between the two medium, that angle of incidence is called critical angle. Done with that? So let us look at lens, right? So some of the students told me that they have a problem with drawing the ray diagrams for lens, converging lens particularly. So let me explain a little bit on that. So the definition of terms here that you need to understand before start to even draw a ray diagram. First one is the focal length. You see the word length. Length means distance. Focal length is the distance between the focal point and the center of the lens. Focal point of principal focus. Focal point is a point which all the rays would be refracted or deflected to. You can write refracted as well. Okay, refracted to where after passing through the lens. Principal axis is a horizontal reference line which must pass through the center of the lens. Why the principal axis is so important? Because principal axis is used in all the measurements. Whether the image is getting larger, image is getting smaller, image is upright, image is inverted. Okay, now let us understand the three rules first in drawing the ray diagrams for converging lens. Let us begin with the first rule. The first rule is all the rays that are parallel to principal axis will be refracted towards principal focus, or sometimes you can call it as focal point. Now I draw this ray. Now this is a lens. I draw it right here. Let's say this is the center of the lens, and this is your principal axis. A ray, a horizontal line, reference line, which passes through the center of the lens. Okay, now ray, this is a two lens, so that is why there are two principal focuses due to the curvature of the lens. Now, the first rule that I explained is actually this one. This is the center of the lens. So any ray that is parallel, that means horizontal, would be refracted towards principal focus. That is how you draw your ray diagram for the first one. Follow the first rule. Second rule, any ray that passes through center of lens will be going straight. the same way as before. Let me draw this as well. This is a lens. Center of the lens is here. This is my principal axis. Now, what do I mean by any ray? Okay, any ray that coming from just anywhere, but it has to pass through the center of the lens. Okay, I'm so sorry. This is not the one. But it has to pass through the center of the lens, which just goes through straight like that. So you have to draw arrow for the ray diagram because the examiner wants to see where is the ray coming from and where is the ray going to. Now the third rule is that any ray that passes through principal focus, okay, before lens. There are two principal focuses. So the ray must pass through the first principal focus first before the lens will be refracted horizontally. Refracted horizontally means it will be going in the same way, okay, as principal axis. This is center of the lens. Okay, there are two principal focuses. So any ray that passed through the first principal focus, let's say pass through, this first principal focus will be refracted horizontally. So when you combine the three rays, you will get the exact location of your image, right? Let us look at this. This is one of the ray diagram. The object is given. So you could see that any ray which is parallel to the principal axis going to the center of the lens will be refracted towards principal focus. Second ray, any ray that passes through the center of the lens which just goes through straight, which is also through. And the third ray, any ray that passes through the principal focus first will be refracted horizontally. Could you see that the intersections of the three rays will give you the exact location of the image? Now, before I list out the characteristics of the image, I want you to see this. This is actually, I'm going to use red color, so it's quite striking actually. This is what we call principal axis. What do I mean by all the measurements are based on the principal axis? Okay, let me explain on that. So you see, this is what the image is being called. You see, if you want to measure the height of the object, you have to measure from the principal axis to where the object is. This is called the height. So I'm also going to measure the height of the image, start from the principal axis to where the image is being formed. The intersections of the three lines. So this is where the image is being formed. So you could see that the height of the image and the height of the object, they're slightly different. And clearly that the height of the image is lower as compared to the height of the object. So one of the characteristics of the image form, it is diminished. Diminished means smaller as compared to the object. And second, you could see that this is the one that object is facing, the side that object is facing, the curve that object is facing is called the front of the lens. When the image is formed at the back of the lens, image is say real image. And one more, you could see the object measured from the principal axis, it is upwards from principal axis to where object is. Now image from the principal axis to where the image is being formed, arrow is downwards. So you can see object arrow is upwards, image arrow is downwards. So that is why we say that image is inverted. Now, these are all the three characteristics of the image that is formed by this ray diagram. Now, okay, the use of the converging lens, or there are many usefulness of the converging lens. So the use of the converging lens is to correct, okay, long-sightedness. Long-sightedness means a person which can see far, long distance, but cannot see the short distance. So the correction, you have to use a converging lens. So I'm drawing an eyeball of a person, the eye of a person. Okay, not good in drawing. Okay, so if you want to correct it, retina is here. Okay, Now, if you want to draw, you have to draw a convex lens like this. This is a ray diagram, how to correct it. So this is center of the lens. So whenever you draw, okay, it will be directed, okay, like that. So I'm going to draw this nicely. Okay, like this, going towards, so all this ray. So this is called converging lens. Okay, this is your retina. And then, okay, the use of diverging lens, or we call it as concave lens, is used to correct short sightedness. So you can see short distance, but cannot see long distance. So I'm going to draw that, how to correct that. Okay, this is your eye. Okay, and then you use a okay. This lens is also called concave. Concave is diverging lens. So it would divert. That means, okay, the ray must be like this. Go towards the lens first, going up. Going out, and then it will be focusing back by your eyeball. So this is it. And then going out a bit. And then, okay, towards out, then coming back. Form at your retina. Now, dispersion. Okay, dispersion is the spreading of white light into 7 spectrum of colors by prism. So this is a prism, white light directed onto the prism. So all the light will be, okay, refracted into 7 different colors. And the main thing for you to bear in mind is that violet, this is violet, this is the red, right? Violet light refracted the most. Red light refracted the least. Do you know why? Violet refracted the most because it is the slowest light. Red light refracted the least because it moves the fastest. It is the fastest light as compared to the 6 different colors. How do I know? Okay, just use the wave equation, V equal to F lambda. The frequency of the white light is constant. That is why the frequency is constant. Red light has the longest wavelength, right? Which is about 600 nanometer to 800 nanometer. Violet light has the smallest wavelength, which is between 300 nanometer to 400 nanometer. So smaller wavelength, slower speed. Larger wavelength, faster speed. That's all. Now, electromagnetic wave. Electromagnetic wave travels with electromagnetic waves, or electromagnetic spectrum travels with the speed of light in air and vacuum. So even in our normal air, they will still travel with the speed of light. The speed of light is 3 times 10 to the power of 8. And then, okay, and it travels with different speed, slower speed at any other medium. Travels with slower speed at any other medium. So you have to memorize the arrangement of the electromagnetic spectrum. Okay, how to memorize? Okay, the first wave is called radio wave, microwave, IR, infrared, visible light, ultraviolet, X-ray, and gamma ray. Okay, now this is towards higher frequency. Bear this in mind, radio wave has the longest wavelength. Okay, longest wavelength. And what is the function of the radio wave? It is used to transmit radio signal. The radio station the radio that you listen every day and transmitted from the radio station, radio signal, and your TV signal, the TV that you watch every day. Right. Why radio wave has, why we use TV signal, why we used to transmit the radio signal? Because radio wave has the longest wavelength, so it can travel further distances. Microwave, on the other hand, is being used apart from cooking, of course. You see this word, keywords, yeah? Satellite communication. Why satellite communication? Because whenever, like, let's say football season, so if you want to watch a live football match, right, from the other country, you're staying in the other countries, right? So that is why you just need to adjust your timing, and then you can watch live show thanks to microwave by using the satellite. That is called microwave. And microwave also being used in our cell phones. Why? Because it has, yes, it doesn't has the longest wavelength, but right, the wavelength is not very small as well. We can make sure that the phone antenna, because it has higher frequency as compared to radio wave, so the phone antenna can be smaller, so the phone can be made lighter. So it's easier for you to carry, portable, right? Infrared, if you can see from barbecue, you grill your food, grill, you can see the red light, that is infrared, or your TV remote control. And your toy cars, remote controls, or your toys with the remote control, that are all called infrared. And then your intruder alarm as well. This has something to do with infrared. Visible light is the light that you can see in everyday's life. And then your traffic lights, they are all visible light. Ultraviolet is used in security situation. Okay, security situation, to identify some of the belongings. Is that okay? And sterilizing medical equipment, or sterilizing water so that you could kill some of the parasite, the germs, right? So that the water that you consume is clean. X-ray is used to check your internal body, like your bones, fracture of your bone, right? Or some of the engineers are using this X-ray to check the tiny cracks in buildings. And gamma ray to treat cancer, because gamma ray has the highest frequency, so it can penetrate more. So these are all about electromagnetic spectrum. So now move on to sound wave. Sound wave, the definition is the vibration, okay, of air particles which are parallel to the direction of propagation of wave. And it consists of a series of compressions and rarefaction. What is compression? Compression means the distance between particles are closer. Rarefaction means the distance between particles are further away from each other. Audible range for the normal healthy human is 20 hertz to 20,000 hertz, or 20 kilohertz. Memorize that. Now, the speed of sound, right? Due to the different medium, the speed of sound will change as well. The speed of sound in air is the slowest. It is between 330 meter per second to 340 meter per second only. But in liquid, because the liquid, you compare between air and liquid, the particles in air are all further apart. So it will take time for this air particle who receive, which receiving the energy to be transferred, the energy to the next air particles. So that is why the speed of the sound is slower. But in liquid, because the particles are closer, so that is why the speed of sound is faster, which is about 1,500 meter per second to 2,000 meter per second. In solid, sound can travel super duper fast in solid, which is about 3,000 meter per second to 5,000 meter per second. That is super duper fast. Don't you think so? But you don't compare with the speed of light. That is even slower, right? When the speed of the sound seems to be slower if you compare to the speed of light. Now, describe a simple experiment for the speed of sound in air, right? The simplest experiment is that, when you want to describe a simple experiment, I would strongly suggest you to draw a diagram. So it's easier for you to see and you can plan your method, right? More organized. I am going to draw this. This is a land. This is a ground. I have two students. One student is holding a pistol and the other student is holding a stopwatch. And this student will be separated by a certain distance. Of course, it is not 1 meter. That is why I'm using measuring tape. Remember, measuring tape is used to measure a distance which is larger than 1 meter. Measuring tape, A and B. So simple experiment, first part, student A holds a pistol. Student B holds a stopwatch. Student A fires pistol and student B starts the stopwatch. And then after that, student B stop the stopwatch when the sound is heard. And then, if you want to say repeat the experiment, repeat the experiment and average is also okay to make sure that the experiment is more accurate. And then 6, speed of sound in air is equal to, speed is distance between student A and B divided by time heard by student B. Done. Oh, yeah, I should highlight the key points for you so that it's easier for you to write down your answer. Whenever you draw a diagram, make sure that you have to label your diagram. It's not about how beautiful you draw a diagram or how real the diagram could turn out to be. It is labeling that is more important. Right? I wasn't born to be an artist, so I wasn't good in drawing a diagram. But as long as I label the diagram, I know that I definitely going to get full marks for diagram. 1 mark for diagram. And then you can say that, student A fires pistol, student B starts the stopwatch, and then the stop when sound is heard. Okay, if you want to say repeat the experiment, yes, you may say repeat the experiment and find the average. Don't just repeat it. And then the speed of a sound is the distance between 2 students and the time measured by student B. Done. Let us move on to loudness and pitch, right? Loudness is depending on, I will split this into 2. So you know that this is about loudness, this is about pitch. Loudness is about, it will affect the amplitude, related to amplitude. right? Higher amplitude. Okay, higher amplitude, louder the sound. Lower amplitude, softer the sound. So whenever a graph is being given, all you need to do is just to look at the y-axis, the displacement. Don't bother about the x-axis. So you see, I got two waves here. I'm going to draw two waves right here. I want you to see carefully. One is blue wave, the other one is red wave. Not so nice. Okay, this one is a bit lower, should be. Okay, I want you to see. Amplitude, look at y-axis. Higher the y-axis, larger the amplitude. Larger the amplitude, that means the sound is louder. So in this case, the graph that I drew, you can say that blue sound wave is louder as compared to the red sound wave. Okay, pitch is related to frequency. Higher frequency, higher pitch. Lower frequency, lower pitch. And then graph given for pitch, look at the x-axis. The x-axis must be time. Right, how do you see? I draw red wave first. Okay, amplitude must be the same. Okay, the other one is blue color wave. Could you see that? So what is frequency? Frequency is a number of complete waves formed in 1 second. So definitely from the diagram that I draw, from the figure that I draw, you can say that red color wave. Red wave, red sound wave, okay, has higher pitch. Why? Because the frequency is definitely higher, because there is no more number of waves formed in 1 second as compared to blue wave. That is all you need to remember about loudness and pitch. Now, echo. Echo means reflection of sound wave. Sound wave also can be reflected because sound is one example of the longitudinal wave, right? So the sound, let's say this is a reflecting surface, could be wall, reflecting surface. So the sound wave would travel towards the wall and then back, okay, reflected back to your ear. This is a person ear so that you can listen to reflection. You can listen to the echo. So the calculation formula, speed of the sound. When you see the word speed of the sound, you see the word echo. Speed of the sound is 2 times the distance traveled by the sound divided by time taken. See that? So when you see the keywords like reflected, okay, going back, travel back in opposite direction to the incident wave. This is called echo, going back. V is equal to 2D over T. That's all. Now, electricity. Let us move on to electric charge and electric current. What is the definition of electric charge? Charge being defined as current multiplies by time, or the product of current and time. Formula Q equal to IT. So Q is measured in coulomb, or capital C. I is called the current, which is measured in ampere. T is called time, which is measured in second. T must be converted to second. And this Q here, Q represents total charge. You see, right, when we talk about charge, there are two charges mainly. One is positive charge, the other one is negative charge. Only negative charge can flow. Only electrons can flow, right? The flow of the electron will give rise to the current. Agree? Now, this Q represents the total number of the electrons. So if they give you, right, the number of the electrons, so you want to relate to the number of electrons, total charge is equal to N times E. What is N? Number of charge particles, mainly electrons. This is a charge of electron because only electron can flow. Right? The definition of electric current is the rate of flow of charge. Current I is equal to Q over T. I must be in ampere, Q must be in coulomb, and then T must be in second. And that is in my direction of current flow is actually from positive to negative. Direction of electron flow is actually from negative to positive, opposite to the direction of flow of the current. Now, electric field. The definition of electric field is a region in which a charge experiences a force. A region, keywords, charge, experience, force. That's it. And electric field flows from positive to negative. Positive to negative, that means like this. If you have, direction of electric field is always positive to negative. In this case, you see, I have two plates, right? So the direction of flow of the electric field is downwards for the first case. Why? Because the positive plate is outwards, the negative plate is downwards. And for the second case, direction of the electric field is upwards because positive plate is below. Now, DC vs AC. I'm going to write this down. Okay. DC means direct current. AC means alternating current. Direct current, current that flows in one direction only. And then alternating current is the current that reverses its direction every half cycle. So I'm going to draw a graph. So the x-axis must be time. So you look at my value. This is time. This is time. Y-axis could be voltage, could be current. So this is time. Could you see that? Now, for the first graph that I drew, all the value of the current is constant at one value, that is DC. Now, the second graph that I draw, all the value of the current is constant at negative value, that is also called DC. Because it doesn't change direction. But for alternating current, sometimes the current is positive value, sometimes the current is negative value. That is called alternating current. So the sources of direct current will be your cell, your battery, your DC power supply. DC power supply. The sources of your alternating current are your AC power supply, AC generator. That. Now, conductor vs insulator. Again, I have to draw table so that I can show you better. Conductor, insulator. Okay, materials that can conduct electricity or heat, yeah? Insulator, material that cannot conduct electricity or heat. So conductor, why conductor can conduct electricity? Has delocalized electrons. Delocalized electrons are the free electrons that are moving inside the metal itself. Okay? Insulator does not have delocalized electrons. And then examples, metal, maybe copper, wire, connecting wires, aluminium, right? So the examples of the insulators are plastic, wood, air, etc. Now, electromotive force, EMF, or Vs, potential difference, which is PD. The definition of EMF and PD are very important, right? So later I'm going to show you the similarity between EMF and PD and the differences between EMF and PD. Now, EMF is being defined as energy per unit charge supplied to move a charge through a complete circuit. PD, on the other hand, is the work done per unit charge to move the charge from one point to another point. Both EMF and PDs are measured in volt. Okay? Now, similarities between EMF and PDs, both are measured in volts. Okay? Both we use the voltmeter to measure. Both are scalar quantities. Those are the similarities between EMF and PDs. And the differences between EMF and PDs, the definition itself is different. So EMF is the one, okay, EMF, okay, is the energy supply. Okay, energy supplied. Oh, I just write down in terms of table. Energy supplied per unit charge. Give me a while. EMF, energy supplied per unit charge in moving or driving the charge through a complete circuit. PD is the work done per unit charge in moving the charge from one point to another. And then, okay, what else? Okay, EMF converts other forms of energy to electrical energy. For example, I have a battery. Battery has chemical energy. So when you connect the battery to the circuit, this chemical energy of the battery will be converted to electrical energy. Could you see that? So this, whereas the PD converts electrical energy into other forms of energy. For example, light bulb. Light bulb needs electrical energy, so it will convert to heat to light after that. Right? So the sources of EMF, battery, cell, power supply, generator, because generator is used to generate electricity. So this one are PDs are resistors, light bulb, filament, LDR, thermistor, or even motor. Now, Ohm's law, George Ohm. George Ohm states that the current or the PD, potential difference, is directly proportional to current at constant temperature. Equation, formula, V is equal to IR. So V is called PD, yeah? PD, I is called current, and R is called resistance. Graph, PD must be measured in volt, current must be measured in ampere, and the resistance must be measured in ohm. Graph, this is PD against current, start from origin. So it has to occur when this graph will be a straight line graph only when the temperature is constant, directly proportional to current. Okay, and just bear this in mind. Resistance is equal to ratio of PD to current. So it's not the gradient of the graph. R is equal to V over I. It is not the gradient of the graph. It is just a ratio between PD and current. Remember that. That's super duper important. Now we move on to relationship between resistance and other physical quantities. Now resistance also can be related to other physical quantity. Resistance is directly proportional to length. That also means that longer the length of the wire or longer the length of the conductor, resistance will also be increasing. But resistance is inversely proportional to cross-sectional area of the wire. Normally we talk about the wire, and I want you to bear in mind cross-sectional area of the wire. Let's say this is a wire. I zoom it bigger. So this is called cross-sectional area of the wire. So we have to imagine that the cross-sectional area of the wire is a circle. It's a circle. So it is related to the area of the circle. So area of the circle that you learn in math is pi r squared. R is the radius. But in our physics lab, we do not have any apparatus that could be used to measure the radius of the wire because the wire itself is very small, right? So we only have the micrometer to measure the diameter of the wire. So diameter has to be related to radius. Radius is equal to diameter over 2. That is why you sub into this equation. A is equal to pi d over 2. You square it. So you have A equal to pi d squared over 4. This is a cross-sectional area of the wire. So combined, you can say that resistance is directly proportional to length but inversely proportional to cross-sectional area, or resistance is directly proportional to length but inversely proportional to pi d squared over 4. Inversely proportional to diameter squared. So these two are very important. So you have to memorize this. Now, electrical energy. right? Energy supply, there are so many energy formula, only 3 energy formulas that you have to bear this in mind. So energy supply, normally we use E equals to VIT. Bear in mind, energy must be measured in joules. So that is why this is called PD, must be measured in volt. This is current, must be measured in ampere, and the time must be converted to second. Energy loss, you can use E is equal to I square R times T, or E equals to V square over R times T. R is the resistance, must be measured in ohm. Electrical power, on the other hand, power is equal to energy over time. Just get rid of the time. IV. This is the most popular electrical power that we normally use for our calculation. I is current, must be measured in ampere. Power must be measured in watt, capital W. And V is the potential difference measured in volt. Power loss, we use P equals to I square R, or P equals to V square over R. Now, thermistor. Seen thermistor before? This is a symbol of the thermistor, rectangular, with the 2 horizontal line here. Horizontal first, then you make a tick like that. That is thermistor. Thermal. So thermistor is related to temperature. So, okay, related to temperature. What happens? Let me write it down. When temperature increases, resistance of thermistor decreases. When temperature increases, temperature surrounding the thermistor increases, the resistance of thermistor temperature decreases, not increases. So sorry, decreases, okay? Decreases. The resistance of the thermistor will have to increase, opposite. Memorize this, okay? Now, LDR stands for light dependent resistor. Light dependent resistor symbol, rectangular shape, horizontal line, arrow, strike it, as if the light is striking on its surface. So light depends on light condition, right? So what to do with it? Okay, when it is bright, resistance of LDR decreases. When it is dark, resistance of LDR increases. LDR is commonly used or widely used in our lampposts. Now, series circuit. Series circuit. Okay, I want you to see this. I'm drawing. Okay, I'm drawing 2 resistors like this. Okay, this is my battery. Okay, resistor 1, resistor 2. Right, series circuit, you have to bear this in mind. Current has only one path to flow. So the current will flow out from the positive terminal, flow into R1, flow into R2, and back into the negative terminal. Right, so the total potential difference is shared between R1 and R2. So this is V1, this is V2. Total PD, I use PD as potential difference, is equal to V1 plus V2. PD across R1 and PD across R2. So I write V total, V1 plus V2. So use Ohm's law. Ohm's law. Still remember? V is equal to IR. So I want to see how the resistors are related. So that is why I sub in V total is equal to I times R total. Currents are the same. Current is this the same current. So that is why I use I R1 plus I R2. So I want you to see this. Cancel the I, so you have total resistance for series circuit is equal to the sum of the individual resistances that are being arranged in that circuit. So you just add it up like normal. For parallel circuit is like this. R1, this is R2, R1, this is R2, and this is the total potential difference. And I want you to see this, right? Current coming out from the positive terminal. This is a junction. What is junction? Junction is a point where the current splits. Is this like the road junction? It is a point where the car will split into, maybe some of the cars will go to the left, some of the cars will go straight, some of the cars will turn right, something like that, right? So the current will split. Some of the current will pass through R1, some of the currents will pass through R2. So the current will be different in this case. And what is the same? The potential different, right, is constant. Bear this in mind because potential difference is measured between these 2 points. Okay, now total current is equal to I1. I say the one that flows to R1 is I1. The one that flows to R2 is I2. So Ohm's law, V equal to IR. So I is equal to R. I is equal to V over R. V over R sub, you have V total over R total is equal to, oh, I just put V because the potential difference is same, V, and then this is V over R1 plus V over R2. So cancel the V, you have total resistance is equal to R total, right? Is equal to 1 over R1 plus 1 over R2, and then you invert it, shift. 1 divided by the answer again. Now, potential divider. Okay, potential divider is something that we use to compare because sometimes, right, when I give you 12 volt, it doesn't mean that you have to use the 12 volt. Sometimes I only need maybe 5 volt. So that is why the potential the potential divider comes into play. So the potential divider is something like this. Okay, you can draw this. And then this is my, okay, V output. This is my V total, and this is R1, this is R2. Bear this in mind, potential divider is only valid to, series circuit. Okay, what happens if I have parallel circuit? You just need to simplify it to become a series circuit in order for you to use the potential divider. Why series circuit? Because current is constant. So potential divider, we use Ohm's law as well. V is equal to IR. But since this is a series circuit, I is constant. So when the I is constant, we just compare V and R. V is directly proportional to R. When the R is larger, the V will also be larger. So how do you form equation based on the diagram that I drew here? You see, I want to find the ratio of V output over the total. How much that I want to use across R2. So V output, since V output is connected to R2, you just put R2 right here, divided by the total V, okay, which is the total R. Total R, because this is a series circuit, so it is R1 plus R2, just like that. Now, fuse, the symbol is like this. Here, pass through the center. So what is the function of the fuse? Function is to protect electrical appliances. Okay, fuse comes with fuse rating, right? So fuse rating, let's say I have an electric kettle, for example. So, or blower, okay, hair dryer, blower. This hair dryer needs only maybe 5 ampere. Right. So I need to have a fuse here just in case, right, the current that flowing through the hair dryer is more than 5 ampere. For example, maybe too much of the current flow because sometimes short circuit might occur and you don't know how much of the current that flows through the hair dryer and you would damage it. It's not cheap to purchase a hair dryer. Don't you think so? But fuse is quite cheap. So you want to choose a fuse rating since the current required for the hair dryer is 5 ampere. So you have to choose a fuse rating which is greater than 5 ampere. Because if you choose fuse rating which is lower than 5 ampere, it is not working because you know why? Fuse rating is the maximum current that is allowed to flow through the fuse before the fuse break. The thin wire inside the fuse break and cuts the circuit. So if I choose the fuse rating may be around 6 ampere, 7 ampere. So it depends on the choices that they gave you. So if you choose 7 ampere, so it will allow the 7 ampere. Of course, it will allow the 5 ampere to flow through it so that the hair dryer can be is workable. So what happens if too much of the current, right? To fuse rating must be higher than current that flows through a little bit higher, must be a little higher than the current that flows through electrical appliance. Okay, so that is the workable. What happens if too much current flows? Let's say this fuse rating is 7 ampere and suddenly there's 10 ampere flowing. So the thin wire in the fuse melts, circuit is cut. It's just like the switch open. Now, magnetic field. Okay, move on to magnetic field. Magnetic field is a region in which a moving charge experiences magnetic force. Magnetic field flows from north pole to south pole. Closer the field lines, stronger magnetic field. Larger the field lines, weaker magnetic field. Now, let me draw the magnetic field around a bar magnet. This is how you're supposed to draw it. Let's say this is a bar magnet. This is the north pole. This is the south pole. Bear this in mind. Magnetic field always flow out from north pole into the south pole. Every line that flow out from north must end in the south pole. So every line. And no magnetic field lines cross. No crossing of magnetic field lines. That means the magnetic field lines cannot intersect. So out from north into south. Right, if you want to see that, like what I said just now, closer the magnetic field line, stronger the magnetic field strength. That means stronger the strength of the strength of the magnet. So magnet, for a bar magnet, the magnetic field will be the strongest at the poles. And bear this in mind, like poles repel, opposite poles attract. So when you draw repel, this is how you're supposed to draw it. So it's just like two magnetic fields are pushing each other away. Let's say north and north. All you need to draw is just to draw upwards like that. To show that they repel each other. It is like they pushing each other away. Something like that. Okay, and then make sure that you draw. This is north. Make sure that you draw magnetic field out from north pole. If these are south poles, then what you need to correct is that for south pole, magnetic field will be inwards. That's the difference. So north and south, for north and south, let's say this is a north pole, and this is a south pole, north, south. Make sure that the magnetic field flow from north to south. That's all. Because opposite poles attract. And one more thing, remember when I define magnetic field, I say a region in which a moving charge experiences a force. Red is related to current carrying wire or current carrying conductor. You know, conductor, let's say this is a wire conductor. When there's a current flowing through it, there will be magnetic field around this wire. This is how you draw the magnetic fields around current carrying wire. Close to the current carrying wire, the magnetic field strength will be stronger. When it gets away from the current carrying wire, the magnetic field strength will get weaker. So how do you determine which direction is the flow of the magnetic field strength? Which direction is the flow of the magnetic field around the current carrying wire? You use your right hand grip rule. Take out right hand. The thumb represents the direction of the current, which is pointing upwards. The four fingers represents the direction of magnetic field. So you just grip it like that, and you can see that the magnetic field flows from this is the direction of the flowing of the magnetic field, anti-clockwise direction. And one more thing, which is very important, you have to bear in mind that the direction of the current is always perpendicular to the direction of magnetic field. Means that when the current is acting straight, magnetic field must be horizontal. That's all. Now, magnetic force can only arise when there are two magnetic fields interact. Okay, so the interactions of two magnetic fields gives rise to magnetic force. So what do I mean by interaction between the two magnetic fields? You see, I have a magnet, for example. These are the two magnets. Let's say this is a north pole, this is a south pole. And you definitely know that the magnetic field will flow from north to south. This is like the magnetic field of the magnets. And I know that I have a current carrying wire which also has its own magnetic field. So I place the current carrying wire with its magnetic field into the region of the two magnets. That gives rise to the magnetic force. So it will cause the wire to be pushed up or down, left or right. Up, down in this case. Okay? Now, Fleming's left-hand rule vs. Fleming's right-hand rule. Fleming's left-hand rule. This is Fleming's right-hand rule. When to use Fleming's left-hand rule? Normally, Fleming's left-hand rule is used to determine direction of magnetic force. Fleming's left-hand rule. The thumb represents, I write down, thumb, index finger, and your second finger. Thumb represents the direction of force. Direction of force. Index finger represents the direction of magnetic field. Magnetic field. Pointing towards south, point to south. And second finger represents the direction of current. Beware, direction of the current is always opposite to the direction of the electrons or beta particles. When to use Fleming's left-hand rule, if a diagram is being given, check for, go on, check for cell, check for battery, check for power supply, any power supply. Because the current need to be flowing in the coil or in the wire. Then only you will have the interactions between the two magnetic fields. Okay, now Fleming's right-hand rule, on the other hand, normally is used to determine the direction of induced EMF or induced current. Now let me write it down. Your thumb, your index finger, and second finger. Thumb, same thing. Fleming's right-hand rule. Thumb represents the direction of the force or direction of the motion that you apply. Direction of force or motion. Index finger is direction of magnetic field pointing towards south. Second finger is the direction of induced EMF or induced current. So when to use the Fleming's right-hand rule? When no battery, no cells, no power supply being given. Power supply being given. And the question asks you to find the direction of the induced current or induced EMF. That is when you use your Fleming's right-hand rule. Right, for both Fleming's left-hand rule and Fleming's right-hand rule, you bear this in mind. Your direction of force, your direction of the magnetic field, and the direction of current are acting perpendicular, 90 degrees to each other. Same goes to Fleming's right-hand rule. Okay? Now, Fleming's left-hand rule on DC motor. So I'm going to draw a DC motor and I will explain the working principle of the DC motor. Now, this is a DC motor. Let's say this is a big magnet. I don't know how to draw the 3D diagram, so you have to imagine. Okay, use your very good imagination. Right here, this is my DC motor. And the main thing about the DC motor, I will label later. I will tell you. Power supply is being given. That is when you know that you need to use Fleming's left-hand rule, north and south. For example. Right, now let me label this first. For DC motor, you have to remember we are using split ring commutator. And this is called carbon brush. What is the function of the carbon brush? Carbon brush is to connect cell or battery, in this case is my battery, to coil so that the current can flow to the coil. This is what we call coil. Coil is normally made from copper. Why? Because copper has a good conductivity. It can conduct better. It's a good conductor. Less heat will be dissipated. Right? And then split ring commutator, the function is, okay, to reverse the direction of current that flows through the coil every half cycle so that coil can turn smoothly in one direction. That's the function of the split ring commutator. It is quite important. Okay, reverse the direction of current so that the coil would turn in one direction. Remember, DC motor, direct current motor uses this split ring commutator. Now let me explain, right? On the working principle of the DC motor, I want you to see the flow of the current from positive terminal flows to the carbon brush, flows through the half part of a split ring commutator. Look at this part. On the left hand side of the coil, look at the left hand part of the coil where the current is flowing into the screen. Now, use your Fleming's left hand rule to determine the magnetic force that acts on the left hand side of the coil. Now, north to south first, your Fleming's left hand rule. The first finger or the index finger is pointing to your right because from north to south, pointing towards south. And the current is into the screen. So the second finger points inwards into the screen. And look at my thumb is pointing downwards. So the force is acting downwards. Yeah. And on the right hand side of the coil, I want you to see this. This is where the current is flowing, flow up and then going down right here. On the right hand side of the coil, use your Fleming's left hand rule again, right? Align your finger, your index finger with the direction of the magnetic field, which is towards right. And the second finger points outwards, coming out from the screen. And my thumb is pointing outwards. I'm so sorry. I don't know how to draw a very nice diagram, right? It might confuse you, but I just want to tell you that the current is coming out. So it's like flat like that. Okay, the current is coming out. I don't know how to draw the 3D, so sorry. And you look at my force, my thumb is pointing upwards. So the force is upwards. Okay, imagine this is like a coil, one up, one down. Could you see that the coil will turn in this direction here? This is the turning direction of the coil, anti-clockwise direction. Okay, now let me explain. First one, current flows through coil, okay, by using Fleming's left hand rule on both sides of the coil direction of forces, direction of forces acting on coil, okay, are shown. You can see one up, one down. Due to two opposite forces acting on coil turn 90 degrees, okay, in anti-clockwise direction. Once the coil has already turned 90 degrees, it will be like that. You know that, okay, between the frame of the coil, there's nothing. There are air particles, but it doesn't cause the magnetic field, okay? It doesn't cut the magnetic field of the permanent magnet. So that is why no force, because no interaction between two magnetic fields, because there's no current flowing through the air particles within the two sides of the coil. So, but the coil will still turn in the same direction. Why? Due to its inertia. What is inertia? Inertia is the tendency of an object to remain in its initial state of motion. The coil is already moving initially, so it will continue to move. That is why the coil will turn. You get me? And then the process will continue when the coil, okay, until you switch off the battery. Okay, I will explain, okay? Once coil is vertical, no interaction between two magnetic fields but coil is still turning in anti-clockwise direction due to its inertia. So that's the reason. Now move on. EM induction, right? Electromagnetic induction states that, okay, the EMF or current induced is always opposing the direction of producing it. This is like the principle of conservation of energy. Energy cannot be created. So you try to produce it, it will try to oppose it. So that is called electromagnetic induction. Induction means production. So induction is that by using magnetic field, you want to produce current. Yes, you can do that. But how, right? Let us look at how. Okay, here I did talk about how to current or PD is being induced. Okay, I will explain this slide first. Now, let us move on to current, how the current or PD, we call it EMF, is being induced. First of all, okay, to produce the current or to produce the EMF, you need to make sure, you need to prepare a conductor and a magnet because magnet has its own magnetic field. Second, you need to make sure this conductor has no current flowing through it. Remember, we are going to produce the current in the conductor. So, it's conductor and magnet must be getting closer or getting away from each other. So the distance between conductor is either getting closer or getting further from each other. Then only we can induce the EMF or the current. I will draw a diagram and I will explain the diagram. Okay, this is like a coil solenoid. I'm so sorry. Okay, I connect solenoid to emitter. There's no current. Emitter is supposed to measure the current. There's no current flowing through the solenoid. And I have a magnet here. This is a north pole. This is a south pole. Push the north pole into the coil. Okay, now what happens? You could see that there is deflections on the emitter. Why? Let me explain. Magnet, permanent magnet, has its own magnetic field, invisible magnetic field that flows out from North Pole to South Pole. You see that? So once you push this magnet into the coil, the invisible magnetic field of the permanent magnet will be cut by the coil. So since the coil is cutting the magnetic field of the magnet, it will change. It will cause a change in the magnetic field of the magnet. It will be different. You cut, so it will be different. So the magnetic field of the magnet would be changed. A changing magnetic field could induce the current in the coil. That is why the emitter deflects. Now let me explain the process. A bar magnet is being pushed into a coil which is being connected to an emitter. Whether the coil is connected to emitter or voltmeter, it doesn't matter. When the current is induced, it also means that the EMF is induced. Right, okay. Now, magnetic field of bar magnet is being cut by coil, which causes a change in magnetic field. According to Faraday's, okay, Michael Faraday's. Michael Faraday states that if there's a change in the magnetic field, current or the EMF could be produced. A change in magnetic field induces current that flows in the coil. Hence, emitter deflected. I will highlight the key points for you. Now, bar magnet push into magnetic field of the bar magnet cut by coil. A change which causes a change in the magnetic field that induces the current, hence emitter induces current in the coil. That is why the emitter deflected. Now let us look at AC generator. AC means alternating generator, alternating current generator. So I have here AC generator, beware. AC generator, okay. Okay, this is the first coil. This is the second coil. AC generator uses, okay, slip rings. So each side of the coil is being connected to each ring. There are two rings all together. And then, okay, connected to this side. Okay, and then you can connect your light bulb right here to see whether the light bulb will light up, right? So what happened is that here, okay, the coil, you have to push the coil first. So when the coil is turning, the magnetic field of the magnet will be cut by this coil. This is coil. This is a carbon brush, carbon brushes here, carbon brushes. These are called slip rings. Okay, this is a bulb. Bulb will light up. Okay, let me explain. When coil is turning, whether it is turning in clockwise or anti-clockwise direction, it doesn't matter, right? Magnetic field is cut by turning coil, which causes a change in the magnetic field. A change in magnetic field induces current or EMF in coil. Hence, bulb lights up. So the graph of AC generator, this is a graph of AC generator per time. You can say this is output current or the output PD or current. So the graph is sinusoidal graph or cosinusoidal graph. You could see that sometimes the output PD is positive, sometimes it is negative due to the direction of the coil that is changing, right? It can turn 360 degrees. Now, Fleming's right-hand rule on AC generator. So I draw an AC generator first because I didn't explain just now, but you have to imagine that this is 3D. So this is slip rings. Okay, let's say I turn the coil in clockwise direction. In clockwise, that means here is upward force, this is downward force. Is that okay? Up and down. Could you see that? Fleming's right hand, this is south. Okay, so what you need to do is, because we are supposed to determine the direction of the induced current, so right hand, my right hand, align, right? North to south. So the first finger is pointing to your right. Second finger is pointing up, no, Your thumb is pointing upwards on the left-hand side of the coil. On the left-hand side of the coil, can you see that my thumb is pointing outwards and my second finger is pointing into the screen? So that is also means that the current induced flows in this direction on the left hand side. And on the right hand side of the coil, because the force is going downwards, still the same. Fleming's right hand rule, north to south, but the force is downwards, so you just twist your thumb a bit, going down. Could you see that? Could you see that? My second finger is pointing at myself, so meaning to say that current is coming up. So these are the directions of the induced current that flows in the AC generator. Now, transformer. Now, the function of the transformer, okay, is to step up or step down voltages. Symbol of transformer. I will explain the working principle of the transformer, no worries. Okay, the ones that connected to AC supply is called primary coil. The one that is connected to maybe light bulb or resistor, this is called secondary coil. And this is called soft iron core. Why we need a soft iron core? Because soft iron core can strengthen the magnetic field. Right, and then soft iron core is a soft magnetic material, so it could be easily magnetized and it could be easily demagnetized. And in the primary coil and the secondary coil, we normally use copper. Why? Because copper is a good conductor. Okay, let me explain the working principle of the transformer. Working principle. First, okay, AC supply has varying current or varying voltage, is up to you. So which causes varying magnetic field around primary coil, and then varying magnetic field of primary coil is being cut by secondary coil, which, almost similar, causes a change in magnetic field of primary coil. And number 3, a change in magnetic field of primary coil causes current to be induced in secondary coil. Okay, hence current flows through, hence resistor. So it is alternating induced current that flows through the resistor. So I'll highlight the key points for you. AC supply, varying magnetic field around primary coil. So this varying magnetic field cut by secondary coil. Change in magnetic field induces current in the secondary coil. That is why AC current flows through the resistor. Though that is what you're supposed to write. And the equation, okay, formula. Vs over Vp is equal to Ns over Np, because Vs means secondary voltage. Secondary voltage is the voltage that is being induced in the secondary coil. Vp means primary voltage. It depends on the number of turns of the coil. Number of turns of, secondary coil. This is not Ns but Np. This is number of turns of primary coil. Memorize this equation. If you don't, because this is just a ratio, it's not really a formula. So therefore, if you put Vp over Vs, make sure that it is Np over Ns. Step down transformer, step out transformer, step up transformer is when number of turns in the secondary coil is more than number of turns in the primary coil. Or, I write here, secondary voltage is larger than the primary voltage. That is being called step up transformer. Step down transformer, number of turns in the primary coil is larger as compared to the number of turns in the secondary coil. Or primary voltage is larger than the secondary voltage. It's like going, then the voltage drop. That is called step down transformer. Now, 100% efficient transformer. Still remember efficiency? The total input that I give must be equal to the output that is given out by this transformer. So this also means that, total input power that flows through the transformer is equal to the total output power. Total input power. Still remember the equation of power? Power is IV. So I input, V input is equal to I output, V output. I input is I primary, V primary. I output, I secondary, V secondary. That is what being said by 100% efficient transformer. Now, advantage, one of the favorite question, popular question is asking about why transmission of the high voltage from the power station is an advantage. Right, first of all, you need to understand that we have a step up transformer that close to the power station. Power station would generate voltage, and then we use a step out transformer to step out the voltage into high voltage and then being transmitted along the wire cables. And before coming into our household, there will be a step down transformer to decrease the voltage to the voltage which is needed by our households. So why transmitting the voltage, at high voltage is an advantage? First of all, I'm going to use the equation or the formula to explain. Seems to be easier. So I would say that the power generated by power station, PG, right? I put the symbol of power generated as PG is equal to IV. So where I represents current, V represents voltage. You can write voltage, you can write EMF, you can write PD. And then to transmit, there will be power loss in transmission cable. Transmission cables. So the power loss is equal to I square R, where R is the resistance of wires, cables. Now, I try to sub into my equation, Power I is equal to power generated divided by V. Can you see that? So I sub into the equation of the power loss. Now my power loss will be equal to power generated over V, and then you square it times R. So you get power generated square over V square times R. And I want you to see this. Power generated by the power station is constant. And then at 240, and resistance of the wire cables is also constant because the wire cables are being used are copper wires. Now you can see that the power loss is inversely proportional to V squared. Can you see that? Since power generated by power station and resistance of wire cables are constant, power loss is inversely proportional to 1 over V squared. So when you step up to very high voltage, power loss could be greatly reduced. When V is high, power loss can be reduced greatly. That's the reason. Okay, now let us move to particle physics. So the first thing about nuclear physics is about alpha particle scattering experiment. Due to this experiment, right, it brings a new revolution to your chemistry. So we know the structure of the atom, we know what is inside the atom. Right, so now the results of alpha particle scattering experiments are first one, most, use the word most of alpha particles pass through the gold foil undeflected. That means, right, you just imagine that you have a thin facial tissue and I have a machine gun, and then every machine gun, my machine gun will give out bullets, and you just imagine that the bullets are alpha particles. So when you fire the machine gun, you fire the bullets towards a thin facial tissue, what do you expect? So if I fire straight, I would expect all my bullets will just go through straight, which is happening right here because most of the alpha particles will just pass through without deflected. But, okay, there's a but, okay, some of alpha particles were being deflected at different angles. So you could see that when you fire straight, you would expect that all my bullets will go to the straight. But I will see that some of my bullet will go to the left, some of my bullet will go to the right. So that is the new discovery. And they have repeated this experiment many times. So they still got back the same result. So that means that this is a new recovery. Right. And the third result, a few alpha particles were being reflected or bounces back at initial path. Right, so I will highlight the keywords here. Most alpha particles pass through undeflected. Some deflect at angles. A few reflected back or bounce back. Right, these are the three results that you need to explain from the alpha particle scattering experiment. Explanation. I explain the first result first. Why most of the alpha particles just pass through undeflected? It is because that inside atom, okay, are mostly empty space. There's nothing. It's just a vacuum, right? The space of the atom inside the atom is basically nothing. It's just vacuum, right? But some of the alpha particles were being deflected at angles. Okay, there must be something because before they conduct the alpha particle scattering experiment, the scientists already know that the alpha particle is a heavy particle and it is positively charged and it carries a large charge as well. Right, there must be something that carries the same charge as alpha particles, light charges, because alpha particle is like being deflected, being slapped away. If there is something inside the atoms which is negatively charged, alpha particles would have been absorbed into the atom. But this is not the case. Alpha particles are like being slapped when it is closer to something inside the atom. Right, so they say that, okay, there is a nucleus, they call it as nucleus, which is small and dense, situated at the center of the atom. Alpha particles that were close to nucleus would be deflected at larger angles, more deflections. When the path of the alpha particles are still far away, less deflection will occur. And the third result, let me explain the third result. How come it is a few means one of the 8,000 bullets or the alpha particles being fired towards the gold nucleus or gold atom, right? One of the 8,000 come back, bounce back, right? This means that the alpha particles which were having head-on collision, head-to-head, okay, were bounced back to their original path. So I highlight the keywords first. Inside atom, mostly empty space. There is a nucleus, small and dense, situated at the center of the atom. Then alpha particles were and also positively charged. Let me add one more. And positively charged. That is why alpha particle will be repelled or deflected. At larger angle, alpha particles head-on collision will be bounced back. So these are all the key points that you have to explain in terms of the results of the alpha particle scattering experiments. Now, isotopes. What's the definition of isotope? Isotope means the nuclide that have the same proton number but different neutron number or nucleon number. For example, 16-8 oxygen, 17-8 oxygen. Could you see that? Okay, these are called proton number. Proton number. These are 16 and 17 are called nucleon number. Nucleon number represents the mass of the nuclide. So if you want to find the neutron number, you take nucleon number minus proton number. 17 minus 8, that will give you 9. The ones that I highlight with yellow color, 8 and 9 are neutron numbers. Now, move on to nuclear fusion and nuclear fission. Definition of these two are very important. Nuclear fusion, fuse together. So two light nuclei combined to form a larger and more stable nucleus. Example, formation of star, how the stars are being formed. And it gives out a large amount of energy. Nuclear fission, on the other hand, is the splitting of a large unstable nucleus into smaller fragments by releasing a large amount of energy. Example, like our nuclear power station. How to generate electricity from the nuclear power station. The keywords are two light nuclei will combine to form larger and more stable nucleus, and it gives out a large amount of energy. And nuclear fission splitting large unstable nucleus into smaller fragments, releasing a large amount of energy as well. So the definition of these two are super duper important. Now let us look at alpha, beta, and gamma decay. Decay means emit. So alpha is called helium nucleus. Remember, it is not helium atom, but helium nucleus, 42He. And it carries positive. The charge is positive 2E. So when a nuclide decay and emit alpha particles, let's say I put 7,3 lithium, for example. Emit, that means you minus 42He. So you balance nucleon number 7 minus 4, you get 3. 3 minus 2, you get 1. Another element is formed. This is what we call alpha decay. Beta is called fast moving electron, 0, negative 1e. That is the electron configuration, and then the charge is negative E. But if this is beta emission, let's say I put 7,3 lithium minus beta, this one you have to beware. This is a symbol of beta, this is a symbol of alpha. And what happened here? 7 minus 0, you get 7. 3 minus negative 1, you get 4. Could you see that? So beware with the proton number of beta. Gamma, this is a symbol of gamma. Gamma is electromagnetic wave. So it has 0 charge. This is a symbol. So when lithium, emit gamma, so you form back, but same nuclear number, same proton number, but it is different element because the energy has changed. That is how you should write your equation for alpha, beta, and gamma decay. But normally we don't put negative on this side, so we move the negative to the other side. So it becomes 73Li form 31Y plus 42He. So same goes to this one. It becomes 73Li form 74Y plus 0, negative 1 beta. And same goes to this 73Li, 73Y plus 0, 0 gamma. Gamma is a form of energy. That's it. Now half-life is being defined as time taken for a radioactive nuclide to decrease to half of its original value or original magnitude or original count rate. So the units of half-lives, it depends on the radioactive isotope. So could be measured in second, could be measured in minute because it is a time, could be measured in hour, days, years, month, etc. So this is the keywords time taken to decrease to half of its original value or original count rate. The symbol of half-life, T 1/2. Now we move on to the last part of the syllabus, which is space physics, right? So you have to understand these terms. Planet, is a large object orbiting a star and clearing its orbit and nearly spherical in shape, nearly. So sometimes to simplify our calculation, we just assume that the planet is a circular planet. Satellite, on the other hand, it is an object which orbit around the planet. It could be natural, like moon is the natural satellite of Earth, or artificial, like a GPS satellite. Asteroids and meteoroids, they are both rocky objects which are way smaller as compared to the planets, and most asteroids can be found in the asteroid belts between the orbits of Mars and Jupiter. Remember that. Now, galaxy, what's the definition of galaxy? Galaxy is a group of stars, dust, and other particles which are held together by strong gravity or strong gravitational force. Now, solar system, the main thing about solar system, you need to memorize the sequence of the planets. So after the sun, the planet that is closest to the sun is called Mercury. After Mercury is Venus. After Venus is Earth. And then after that, Mars. And then Jupiter, Saturn, Uranus, and Neptune. So Mercury, Venus, Earth, and Mars are called small planets. Small planets. Small planets or rocky planets. They consist of rocks. But Jupiter, Saturn, Uranus, and Neptune, they are being called large planets or huge planets, mainly consist of gas. We move on to the phases of the moon. So the main thing about the phases of the moon, which often came out, is the location of the new moon and the location of the moon when it is being called full moon. So bear this in mind, new moon occur when the sun, not the sun, the moon is between the sun and the earth. That is being called new moon. Full moon is when the earth is between the sun and the moon. So same goes to waxing crescent, first quarter, waxing gibbous. It is suggested that you better memorize, just in case. Now, one light year is being defined as the distance that is being traveled by the light in one whole year. So if you want to calculate the value of one light year, you just recall speed is equal to distance over time. That distance is called 1 light year. So distance is equal to speed multiplied by time. The speed of light is 3 times 10 to the power 8. 1 year is 365 days. 1 day 24 hours. 1 hour 60 minutes. 1 minute 60 seconds. And you just times it. 3 times 10 to the power 8 times 365 times 24 times 60 times 60. And you get 9.46 times 10 to the power of 15 meter. This is the value of 1 light year. You need to know how to prove it. Now, life cycle of a star. For a life cycle of a star, just consider whether the question is asking about small size star or medium size star. Or the question could ask about the giant star and super giant star. Right. For life cycle of a small or medium-sized star, everything starts from nebula, a cloud of gas, and then goes to protostar, right? So protostar, you can see the shape of the star. It's like a globe like that. And then main sequence star. Main sequence star is called a stable star at the same time because the process of fusion has already occurred. and it goes to red giant, and after red giant, that is called white dwarf. For life cycle for the big or supermassive star, everything starts from nebula first. After that, protostar, then main sequence. After main sequence, it goes to super red giant, even larger, right? Due to the multiple cycle of the fusion that occur, and then it is the helium gas that carry on the process of fusion. And after that, supernova, a large explosion, which gives out a huge amount of light, and then it could be turned on to neutron star or black hole. Now, how are planets formed using accretion model? So I want you to write this down. It is actually start from the dust and gas particles which have low density rotate around a young star, a very young star, and collide with the star and stick together in elastic collision. And what happens after or over millions of years? These particles grow bigger and forming planet. Now, how distant galaxies give evidence to support Big Bang theory? The answer is only redshift, but I will explain redshift. So the galaxies, the galaxies are moving away from Earth. And while moving, distance galaxies give out light that is stretched towards the red end of spectrum, proving that they are receding. So why red? Look at the colors. There are 7 colors altogether. Red light has the longest wavelength. So when the galaxies are moving away, they will give out light. But due to the distance is getting further and further away, so it will give out light in terms of red color. That means stretch towards the red end of the spectrum because red color has the longest wavelength. That is being called redshift. Okay, now there are 3 regions of electromagnetic spectrum which the sun emits the most energy. What are the 3 regions? First region is called visible light. Visible light is the light that you can see, all the 7 colors. Second is called UV, ultraviolet ray, and the third is called infrared. So these are the 3 regions of the electromagnetic spectrum which the sun emits the most energy. Remember that. Now move on to Hubble's law. So Hubble's law states that the speed at which the galaxy recedes or moving away is directly proportional to the distance between the galaxy and the Earth. That is Hubble's law. And Hubble constant. So you see Hubble's law is this, okay? We put a constant, right? The Hubble constant, this is called Hubble constant. H naught is called Hubble constant. To get rid of the proportionality, we have to put equal to a constant, right? Hubble constant is the constant of proportionality, which relates to the Hubble's law, giving the rate of the expansion of the universe. So from the Hubble constant, right, you can calculate the age of the universe. Now, redshift, it is the increase in the wavelength which is shifted toward the red end of the spectrum of light from the galaxies which are moving away from us, indicating the universe is expanding. Now, CMBR, cosmic microwave background radiation. It is a weak radiation detected in all directions, considered the leftover energy from the Big Bang. And it is also formed, okay, it also being detected right after Big Bang. It is the key evidence, right, for the Big Bang theory. So that is all about IGCSE Physics Paper 4, the final boost. Right, if this video helped you to connect the dots and feel more confidence about your IGCSE Physics Paper 4, don't just stop here. On this channel, I break down IGCSE Physics, the way the examiners test it, not just theory, but how marks are awarded. So if you are serious about improving your IGCSE Physics grade, subscribe now and turn on the bell because your future videos might be different between just passing and getting the grade you want. You have got this. All the best.